Welcome, friends. He is so glad they are here. Whether they are drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, they have found the right place. Before the journey begins, he would love to know where in the world are they listening from. Perhaps they are wrapped in a blanket sitting by a softly lit window, or resting somewhere under an open sky. Wherever they are, he hopes they are warm, comfortable, and ready to wander with him into reality itself, into the strange possibility that the world's deepest rules may be simpler than they look, and yet still beyond dismissal. If they find peace or curiosity in these gentle stories, he invites them to consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The voice stays whisper soft, and the first image is not a computer screen or a thought experiment, but a night sky with quiet stars and a planet beneath it that feels solid, heavy, familiar. Earth turns with no visible seams, oceans flowing, clouds forming and dispersing stone, warming in sunlight and cooling again in shadow. It appears continuous like one unbroken surface. Yet the accepted fact of modern physics is that much of nature is quantized. Energy levels in atoms come in discrete steps, electric charge comes in fixed units, and quantum fields underpin what later becomes matter and light. The narrative does not argue for a simulation. It simply notices the texture of reality as science describes it, where smoothness is often an emergent illusion of scale. Only took a microscope and a few centuries of physics to discover that continuous can be a convenient approximation. Beneath the night sky, the planet's materials are made of atoms, and atoms obey quantized rules. Electrons occupy orbitals with specific energies, not any energy they please. Photons are exchanged in discrete packets. Spectral lines appear as sharp signatures because atoms and molecules have quantized transitions. This is accepted, measured, and used every day in laboratories and telescopes. It is one of the first quiet reasons some people feel the world resembles something computed. It can be described in symbols, and it has granularity. Yet a quiet scientific mystery is present immediately, and it remains unresolved in a deep sense. Why are the fundamental constants of nature, like the fine structure, constant particle masses, coupling strengths, set to the values they have? Physics can measure them with extraordinary precision, and it can show how changing them would change the universe, but it does not yet provide a complete explanation for why they take these particular values rather than others. Only took a universe that works at all to make why these numbers a question that refuses to go away. The narrative stays grounded and turns its gaze downward from stars to stone. Earth's crust is a mosaic of minerals, and minerals are the planetary expression of atomic order. In a crystal, atoms occupy repeating positions in a lattice, forming patterns that are rigid, regular, and countable. Quartz grows as silicon and oxygen arrange into a framework. Feldspars align their tetrahedra. Olivine stacks magnesium and iron with silicate groups in a structure that can be measured by X-ray diffraction, turning invisible order into visible peaks on a graph. This is accepted solid-state physics and mineralogy. The planet's rocks are organized matter, and their organization is discrete at the atomic scale. A lesser-known detail lingers in the way. Crystals sometimes record growth in zones, subtle bands of composition reflecting changes in temperature or chemistry during formation, as if the mineral keeps a faint diary of its own environment. Only took a cooling melt to write stripes inside a crystal no eye will see without slicing it thin. The narrative keeps the tone even, letting a quiet irony settle in without changing pace. The first irony is that Earth's most solid substances are built from mostly empty space atoms, separated by distances far larger than they are nuclei held together by electromagnetic fields that are not solid in any ordinary sense. The second irony is that the planet feels continuous underfoot, yet its strength comes from quantized bonds and latticed effects, tiny discontinuities that decide whether rock breaks or holds. The third irony drifts in softly. The more precisely reality is measured, the more it resembles a set of rules, and rules always tempt the mind to imagine a rule maker even when none is required. Only took a few equations to make philosophy unavoidable. The narrative then approaches the idea of a grid beneath reality not as a claim, but as an image for how physics describes measurement. Space and time at everyday scales behave as continuous variables, yet in many approaches to quantum gravity still incomplete and not yet experimentally confirmed, there is the possibility that space-time itself may have a discrete structure at extremely small scales, perhaps near the Planck length. This remains speculative, not a consensus fact. What is accepted is that general relativity describes spacetime as smooth and continuous, while quantum mechanics describes fields and interactions with quantization, and these frameworks are not yet fully unified. This is the section's quiet scientific mystery: how to reconcile gravity with quantum physics in a single consistent theory, and whether spacetime is ultimately continuous or discrete. Only took a century of brilliant physics for the two best theories to still not fit perfectly together. The narrative keeps Earth present as an anchor, because Earth is not an abstraction. It is a world of heat flow and phase transitions and chemical cycles. The solid crust rests above a convecting mantle, and that mantle behaves like a fluid over long timescales, even though it is solid rock, because temperature and pressure allow slow deformation. This is accepted geophysics. Mantle convection drives plate tectonics, moving continents and recycling crust. The planet's large-scale behavior emerges from countless small-scale interactions, atoms vibrating, defects moving, minerals deforming, none of which need to be computed by a machine to occur, and yet all of which can be modelled computationally because the rules are consistent. A gentle modern analogy can hover like weather, where simple physical laws generate patterns that look endlessly complex yet remain lawful. Only took a few equations for storms to feel unpredictable while still being physical. The narrative holds the simulation idea at the edge without letting it take over. It notes that the universe is mathematically describable to an extraordinary degree, and that this compressibility of nature into laws is itself a philosophical wonder. But it also notes quietly that describable does not mean designed and computable does not mean computed. The map can be drawn without implying a mapmaker. Still, the mystery remains: why does mathematics fit nature so well? This is not a settled scientific question. It is a long-standing puzzle in the philosophy of science. Only took humans discovering patterns to wonder why patterns are discoverable. The narrative returns to a more physical scene to keep the tone grounded. In a dark volcanic landscape, basalt cools and contracts, forming hexagonal columns, a pattern born from fractures as the rock shrinks. The columns look like deliberate architecture, yet they form from stress distribution and crack propagation without a plan. This is a real geological process seen in places like Giant's Causeway and Devil's Postpile. The pattern is a reminder that structured outcomes can arise from simple constraints. A lesser-known detail: the spacing and size of the columns depend on cooling rate, with slower cooling often producing larger columns, as if the rock's geometry is paced by time. Only took a slower loss of heat to make larger polygons. The narrative lets this be a soft callback to the idea of pixels and grids, but it keeps it in stone rather than metaphor. It also keeps a quiet uncertainty alive, even in well-studied fracture mechanics. Predicting the exact patterning of cracks in complex natural settings is difficult, because small variations amplify. The world follows rules, but it does not always yield exact outcomes to prediction. Only took deterministic laws and chaotic sensitivity to make certainty rare. The section ends by holding Earth and physics in the same frame, a planet that feels continuous, yet is built from discrete bonds, a reality that can be modelled yet still surprises, a set of laws that appear consistent yet are not fully unified with gravity, constants measured with precision yet not explained in origin. Simulation theory remains for now, an interpretive shadow at the edge of these observations, a way some minds try to name the strangeness of a lawful world. The narrative does not endorse it, and it does not dismiss it. It simply begins in the only honest place with what is known, with what is measured, and with what remains quietly unanswered, like starlight that reaches the eye without explaining why it exists at all. The planet remains under the same quiet sky, and the narrative moves from the broad idea of quantization into the tangible intimacy of minerals, because if reality is ever pixelated, the most honest place to see it is not in philosophy but in stone. Earth's crust is a mosaic of crystals, and crystals are matter arranged as a repeating decision, this position, then this position, again and again, until a grain becomes visible. The accepted fact is that atoms in a crystal occupy a lattice, a regular structure defined by bonding and energy minimization. This is not merely a model, it is measured by diffraction, by spectroscopy, by microscopy. In a cooling magma, minerals nucleate and grow when temperature and composition cross stability fields. Basaltic magma crystallizes olivine and pyroxene early. More evolved magmas crystallize feldspars and quartz. This is accepted. Petrology mineral assemblages reflect thermodynamic conditions and the chemical makeup of the melt. Only took a melt cooling by a few hundred degrees to turn a fluid into a rock with geometry. The narrative lingers on the way crystals grow because growth is a slow accumulation of discrete units. In a crystal lattice, atoms and ions attach to surfaces in steps. Growth fronts advance layer by layer, sometimes leaving terraces and spiral patterns around dislocations, defects that allow crystals to grow continuously even when perfect flat layers would require too much energy. These spiral growth patterns are real and can be seen under microscopes in certain crystals. A lesser known detail rests here. The presence of dislocations can both weaken a crystal and enable its growth, meaning imperfection becomes a mechanism of formation. Only took a flaw to help build a perfect-looking gemstone. The narrative holds that as a soft callback to simulation-like thinking systems often require irregularities to function, and the world's apparent smoothness is supported by microscopic brokenness. The ironies arrive quietly and dryly. The first irony is that crystals' icons of order are full of defects, vacancies, impurities, dislocations that determine their strength, color, and behavior. The second irony is that a planet's most durable record keepers are tiny crystals that survive tectonic recycling precisely because they are hard and stubborn, while the grand landscapes that seem permanent are erased. The third irony settles: the more orderly the lattice, the more easily it can shatter along planes of weakness, as if order comes with built-in fracture lines. Only took a lattice plane to decide how a rock breaks. The narrative moves deeper into the idea of discreteness by staying with atoms themselves. Atoms are stable because electrons occupy quantized states around nuclei, and those quantized states arise from the wave nature of particles in quantum mechanics. The accepted fact is that quantum mechanics predicts discrete energy levels in bound systems, and that prediction matches observations such as spectral lines and the periodic table's structure. The periodic table is not just a list, it is a map of how electron shells fill according to quantum rules. This is why oxygen bonds the way it does, why silicon forms tetrahedra in most silicates, why iron can exist in multiple oxidation states, and why minerals have the structures they have. In this way, Earth's geology is quietly an expression of quantum behavior, written large in continents and seafloors. Only took electrons choosing allowed states to determine what kinds of rocks exist. Yet a quiet scientific mystery sits inside this accepted framework. Why do quantum laws take the form they do, and why do they permit stable atoms rather than a universe where electrons spiral into nuclei, or no chemistry is possible? Quantum electrodynamics explains stability with great precision, and yet the deeper why these laws question remains open. It is not the kind of mystery that can be solved by one measurement. It touches the foundations of theory. Only took a universe capable of chemistry to make why chemistry is possible a legitimate question. The narrative remains grounded by returning to a physical scene of formation. In a magma chamber beneath an early volcanic arc or beneath a plume-fed basalt province, melt cools slowly enough for crystals to grow large. Feldspar crystals can develop zoning with concentric bands that record changing composition of the melt over time, variations in calcium, sodium, potassium. These zones can be read like contours of a vanished thermal history. In some cases, crystals trap tiny inclusions of melt or fluid sealed inside as the crystal grows. These inclusions preserve the composition of ancient magmas and volatiles acting like microscopic time capsules. A lesser-known detail, fluid inclusions in certain minerals can preserve ancient water and gas compositions, sometimes with tiny bubbles that expand or contract with temperature like miniature atmospheres locked in stone. Only took a crystal growing around a droplet to preserve a sample across deep time. The narrative lets this detail linger because it demonstrates an almost information-like property of matter. Structures can store traces of conditions. This is not mystical, it is physics and chemistry. Yet the concept naturally brushes against the language of information, and information is one of the bridges simulation theory tries to build. The narrative stays careful. It observes that matter can store information in arrangements, lattices, defects, isotopic ratios, without implying an external storage device. Still, the mystery remains. Why is the universe so hospitable to stable records? Why do processes leave traces that can be read? Only took entropy increasing for some traces to become irreversible. That brings the narrative to thermodynamics in a quiet way. In crystal, growth order increases locally as atoms arrange into lattices, yet entropy does not decrease overall because heat is released and the environment's entropy rises. This is accepted. Local decreases in entropy are allowed when energy flows and total entropy increases. The planet is full of such processes. Snowflakes form intricate patterns while heat disperses. Minerals crystallize while magma releases heat. Life builds order while dissipating energy. The narrative lets a gentle modern analogy hover, like organizing a room while generating a pile of discarded packaging outside. Order appears in one place while disorder grows elsewhere. The analogy is kept soft and not turned into instruction. Only took energy flow to make order feel effortless in one place and costly in another. The simulation idea remains at the edge because one of its appeals is the intuition that information and computation underlie physics. Some modern theoretical work indeed explores deep connections between information and physical law, black hole entropy, holographic principles, quantum information frameworks, but the narrative remains anchored to scholarly caution. These are active research areas, not settled proof of anything like a simulation. The quiet uncertainty here is real. What is the most fundamental description of reality? Is it fields, geometry, information, something else? The theories are mathematically rich and the experiments are difficult. Only took the smallest scales being inaccessible to make the largest ideas uncertain. The narrative returns again to Earth's mineral world to avoid drifting into abstraction. In metamorphic rocks, minerals transform when pressure and temperature change, reorganizing their lattices into new stable forms. Graphite can transform into diamond under high pressure, the same carbon atoms rearranged into a different lattice. This is accepted mineral physics. Diamond is metastable at Earth's surface but stable at depth. Graphite is stable at low pressures. The transformation is a rearrangement of bonds, discrete changes producing macroscopic differences in hardness and optical properties. A poetic detail rests in how diamonds can carry inclusions from deep mantle environments, minerals that only form at high pressure, offering direct evidence of deep earth conditions. Only took carbon rearranging to become a courier from the mantle. Yet even here there is uncertainty interpreting diamond inclusions, and their depths requires models of pressure-temperature conditions and can carry ambiguity. The narrative holds that as another soft reminder, even when the lattice is known, the story behind it can remain partly hidden. The section closes by letting the listener's attention rest on a single grain of rock imagined not as a metaphor but as a real object, a crystal lattice repeating in silence, defects, threading through, isotopes sitting in fixed ratios, intrusions holding ancient fluids, all of it assembled by energy minimization and time. If reality ever resembles a simulation, it is in this sense the world follows rules that can be described, and those rules produce discrete structures that store traces. Yet the deepest question remains unanswered and deliberately unforced. Why these rules? Why these constants? Why a universe where atoms can form, where crystals can grow, and where a planet can carry so much quiet information in stone? The mineral grain remains in mind, quiet and structured, and the narrative lets it become a bridge to time. Because Earth is not only made of matter arranged in lattices, it is made of durations measured not by calendars, but by decay. The accepted fact is that radiometric dating works because certain isotopes are unstable and decay into daughter isotopes at statistically predictable rates described by half-lives. Uranium decays to lead potassium-40 decays to argon-40, rubidium decays to strontium-samarium to neodymium, and these systems, among others, allow scientists to date rocks and minerals across deep time. This is not a philosophical claim. It is a practical tool that has built the timeline of Earth's formation and evolution with remarkable consistency across independent methods. Only took unstable atoms quietly falling apart to give the planet a clock. The narrative stays slow and lingers on how a radioactive clock is written into stone. When a mineral crystallizes, it can incorporate certain elements into its lattice while excluding others. Zircon, for example, readily incorporates uranium but rejects lead when it forms so. Any lead found later in the zircon is likely radiogenic, produced by decay. This is accepted geochemistry, and it is why zircon is such a powerful timekeeper. Potassium-bearing minerals can trap argon, and when heated above a closure temperature, argon can escape resetting the clock. When cooled, argon accumulates again. Different minerals and isotopic systems, therefore, record different aspects of a rock's history: formation, cooling, metamorphism, alteration. Time is not one number. It is layered like the rock itself. A lesser-known detail rests in the concept of discordance, where zircon show mismatched uranium-lead ages because lead has been lost during later heating or alteration. Geologists use Concordia diagrams to interpret these patterns, extracting both original crystallization ages and later disturbance ages from the same grain. Only took a crystal being slightly leaky to record 2 times at once. The narrative lets this detail settle as a quiet demonstration that the world stores history in subtle ways, and that reading history requires model and humility. The ironies arrive softly dry and sleepy. The first irony is that the most reliable clocks on Earth are built from instability. The atom's willingness to change becomes the planet's way of remembering. The second irony is that the deeper the time, the more precise the measurement can be, in some cases millions of years, resolved in a grain, while human memory struggles with a single decade. The third irony is that people often ask for certainty about the past, yet even the best clocks must be interpreted, corrected and cross-checked because the rock can be altered, reheated or partially reset. Only took the planet being active to make its own timeline a puzzle. The narrative now pauses on the nature of decay itself, because decay introduces a quiet conceptual hinge. Radioactivity is governed by quantum mechanics, and quantum mechanics is probabilistic. An individual nucleus does not decay at a predictable moment. It has a probability per unit time of decaying, and half-life describes the statistical behavior of many nuclei. This is accepted physics. It is not that the universe lacks law, it is that the law is statistical at the fundamental level. Here the section's scientific mystery appears quiet and fundamental. Why are quantum outcomes probabilistic? Interpretations vary. Copenhagen many worlds objective collapse models, hidden variable theories constrained by Bell's theorem, and while quantum mechanics is extraordinarily successful in prediction, the meaning of probability in it remains debated. This uncertainty is not a gap in measurement, but a deep question about what reality is doing. Only took the best-tested theory in physics to still leave room for interpretation. The narrative keeps this close to Earth by noting how radiometric clocks depend on this probabilistic foundation. The planet's age, the timing of impacts, the tempo of tectonics all are anchored by the decay processes that are random in the small and regular in the large. If simulation theory feels tempting here, it is because randomness and discreteness can resemble algorithmic choices and random number generation. Yet the narrative remains careful. Quantum randomness is not known to be pseudo-random, and experiments testing Bell inequalities strongly suggest that any underlying hidden variables would need to be non-local or otherwise unusual. The world's randomness appears fundamental in many standard interpretations. Still, the deeper question remains, is quantum randomness truly intrinsic, or is it emergent from something deeper? Only took a coin flip at the nucleus scale to make determinism feel like a question rather than an assumption. The narrative returns to Earth's deep time record because Earth's story depends on these clocks. Meteorites provide ages that cluster around 4.56 billion years, defining the solar system's formation. Earth's oldest minerals reach about 4.4 billion years in some zircons. The oldest known rocks are younger because early crust is recycled and transformed. These are accepted constraints even if specific samples and interpretations can be debated. Radiometric clocks also show the timing of major events, the stabilization of cratons, the ages of mountain belts, the opening and closing of ocean basins. Time becomes measurable in the planet's fabric. A poetic detail rests in the idea that each mineral grain contains a population of atoms that have been decaying since the grain formed each nucleus, a tiny quiet countdown that no one hears. Only took billions of silent decays to make a number on a lab instrument. The narrative then lingers on the concept of closure again because it is a subtlety that makes Earth's time record layered rather than simple. A metamorphic rock can contain minerals that record different times. One mineral might preserve the age of original crystallization, another might record the time of metamorphism, another might record cooling through a certain temperature. In this way, a single rock can be a stack of timestamps. This is accepted metamorphic geochronology. Yet uncertainty remains in interpreting complex histories. Diffusion can blur signals. Fluids can introduce new elements, deformation can create pathways for loss. The quiet scientific mystery is not whether clocks work, but how to read them correctly in the most complex settings and how to quantify uncertainties honestly. Only took one fluid pulse through a rock to complicate a billion years. The narrative now allows a gentle modern analogy like a long-used notebook, where some pages are rewritten, some are smudged, and some are preserved perfectly. Earth's rocks carry time with edits and erasures. The analogy stays soft and does not become a story device. It simply helps the mind accept that history can be both real and partially overwritten. The simulation theme stays at the edge and it touches time in a particular way. In computation, time is often advanced in steps, ticks of a clock, frames of an update. In physics, time appears continuous in classical theories, yet quantum events like decays occur as discrete transitions between states. This resemblance is not proof, only a resemblance. The narrative notes quietly that nature's updates are not synchronized to a global clock in any known way. Decay events are independent and their timing is probabilistic. Still, the mind notices patterns, discrete events, statistical regularities, lawful evolution. The deeper question remains open. Is the universe fundamentally digital, analog, or something that does not fit the human metaphor of either? Only took human metaphors to feel both helpful and insufficient. The narrative returns to the arrow of time, introduced gently but not fully explored yet, because decay also points in one direction. Parent isotopes decrease, daughter isotopes increase. This seems like a direction in time, though the fundamental laws of physics are often time-symmetric at microscopic scales, with some exceptions like CP violation in certain weak interactions. The arrow of time in many accounts emerges from thermodynamics and the low entropy condition of the early universe. But why the early universe has such low entropy is still debated. The narrative holds this as an unresolved question that will echo later. Why does time have a direction that the world seems to follow so reliably, from hot and mixed toward cooler and more differentiated, from simple toward structured, from fewer traces toward more traces? Only took entropy to make before and after feel different. The section ends by returning to Earth's quiet measurement culture. In a lab, a zircon is mounted, polished, and hit with a tiny laser or ion beam, releasing atoms that are measured in a mass spectrometer. Ratios become ages. A planet's eons become numbers. It is a remarkable compression, 4 billion years reduced to digits and error bars. This compressibility is one reason simulation talk persists. Reality seems to fit into information. Yet the narrative remains grounded and neutral. The ability to describe is not the same as the thing described. The zircon's time is real whether or not it is written down. The decay events happen whether or not they are counted. The world continues lawful and quiet, and the deepest mystery remains. Why the universe's smallest events are probabilistic, and why those probabilities align so well in aggregate to give Earth a reliable sense of age, as if the planet carries its own metronome in the silent breaking of nuclei. Time now feels present in the stone, not as an idea but as a direction, and the narrative follows that direction into heat, because Earth's earlier story is written first in temperature and only later in crust and ocean. The accepted fact is that the young Earth is hot from accretion differentiation and radioactive decay, and that it cools over time by radiating heat to space and by transporting heat from the interior through convection and conduction. This cooling is not a straight line. It is mediated by atmosphere's impacts, mantle dynamics, and the formation of insulating crust. Still, the overall trend is clear. The planet begins far hotter than it is now and gradually loses heat. Only took 4.5 billion years for a molten beginning to become a mostly solid surface, which is an unhurried way to cool. The narrative stays in the Hadean imagery without repeating earlier explanations, letting molten rock stand again as a quiet elemental presence. A magma ocean can exist after major impacts and during early accretion. As it cools, crystals form, settle, or float, and the mantle differentiates chemically. Heat moves upward and the surface radiates into space, but the atmosphere above can trap heat. The accepted process of greenhouse warming applies here as well. Water vapor and carbon dioxide absorb infrared radiation, slowing cooling. This interplay between interior heat and atmospheric insulation is a real part of early Earth modelling. Yet uncertainty remains in the durations. How long do magma oceans persist? How thick are early atmospheres? And how much does repeated impact remelt the surface? Only took one impact to reset a cooling curve, and early Earth has many chances to do exactly that. The narrative turns toward thermodynamics because thermodynamics is the language of heat and time's direction. The second law of thermodynamics states that in an isolated system, entropy tends to increase. Earth is not isolated. It receives energy from the sun and radiates energy to space, and it also has internal heat sources. Yet within Earth's processes, energy tends to disperse from hot to cold, gradients tend to smooth unless maintained, and irreversible processes leave traces. This is accepted. The arrow of time in everyday experience is closely tied to thermodynamic irreversibility. A basalt flow cools and solidifies. It does not spontaneously remelt into a flowing river without added energy. A crater forms, it weathers away, it does not reassemble into a pristine rim. Only took irreversible processes to make past feel like something that cannot be undone. The narrative holds a quiet scientific mystery at the heart of this. Why does the universe begin in such a low entropy state that allows an arrow of time to be so pronounced? Many explanations are proposed: cosmological initial conditions, inflationary scenarios, gravitational entropy considerations, but there is no single universally accepted, experimentally confirmed account of why the initial condition is so special. Physics can describe entropy growth given an initial condition, but the origin of that initial condition remains open. This mystery is fundamental, and it touches simulation talk without requiring it. A simulation would have initial conditions chosen by something external. But in physics, the initial condition is simply a fact to be explained if possible within the universe. Only took the cosmos starting ordered enough to make everything else possible, so the narrative stays grounded by returning to Earth's cooling rock because the arrow of time is visible there. As magma crystallizes, it releases latent heat, slowing cooling, and the resulting minerals record the cooling path. Certain textures in igneous rocks, like crystal sizes and intergrowths, reflect cooling rates, a quiet time signature written by heat flow. A lesser-known real-world detail rests in the way some volcanic glasses like obsidian are metastable. Given enough time and the right conditions, they devitrify, forming microscopic crystals transforming from glass to fine-grained rock. This is not dramatic. It is slow. The glass is a frozen snapshot of a melt, and devitrification is the planet's way of continuing to relax toward equilibrium. Only took thousands to millions of years for glass to admit it wants to be crystal. The narrative lets that become a gentle metaphor for irreversibility states. Relax, gradients fade, and the world moves toward equilibrium locally, even as energy flow maintains complexity elsewhere. The ironies arrive softly again. The first irony is that the planet's early heat, which seems like pure disorders, is also what allows differentiation and layering order emerging from a hot beginning. The second irony is that the arrow of time feels obvious in daily life, yet its ultimate origin remains one of physics' deepest open questions. The third irony is that humans build machines to reverse small processes, refrigerators, engines, computers, yet the total ledger still obeys thermodynamics and the cost is paid in heat dumped elsewhere. Only took a refrigerator to prove that cooling something requires warming something else. The narrative now threads simulation theory gently through thermodynamics without stepping into fiction. In computation, erasing information has a thermodynamic cost captured by Landauer's principle, which links information theory to physical entropy deleting. A bit of information dissipates a minimum amount of heat. This is a real result in physics tested experimentally in various forms. It suggests that information processing is not separate from physics. It is physical. This is one reason some thinkers speak of it from bit or of information as foundational. Yet the narrative remains cautious. Such connections do not imply that reality is literally a simulation. They show that information and thermodynamics are intertwined. The quiet uncertainty is what to make of this entanglement. Is information fundamental, or is it a convenient description of physical states? Only took one principle about erased bits to make metaphysics feel close to engineering. The story returns to Earth as the dissipative system because Earth maintains patterns by exporting entropy. The planet receives low entropy energy from the sunlight at a high temperature and radiates higher entropy infrared energy back to space at a lower effective temperature. This difference allows Earth to maintain gradients and structures, weather systems, ocean circulation, life. This is accepted. Earth is not violating thermodynamics. It is using energy flow to sustain local order while increasing entropy overall. A gentle modern analogy can hover like a candle flame maintaining a steady shape while constantly consuming wax and releasing heat and light. Earth's organized systems persist by continuous throughput. Only took a steady energy source to keep patterns from fading. The narrative then lets the Hadean imagery fade slightly and brings forward the concept of directionality in Earth's history. Cooling allows oceans to condense crust to stabilize tectonics to develop and life to persist. In this sense, Earth's story has an arrow, not because it is aimed, but because physics allows a sequence of phase transitions and chemical thresholds as the planet's thermal state changes. Yet uncertainty remains in the exact pathways early tectonic regimes' atmosphere composition impact histories all vary in models. The arrow points from hot to cooler, but the route is winding. Only took 1 billion years for the planet to stop being mostly molten, and even then it keeps pockets of melt and heat inside forever. The narrative keeps a quiet callback to the earlier quantum discussion decay as probabilistic, yet the arrow of time feels deterministic. This juxtaposition is one of the strangest textures of reality randomness in the small directionality in the large. In simulation metaphors, one might imagine random seeds and deterministic update rules. In physics, one sees probabilistic quantum events and emergent thermodynamic behavior. The deeper mystery remains how exactly does classical irreversibility emerge from underlying microscopic laws, and what role do measurement decoherence and coarse graining play? This is an active area of foundational research. Only took ignoring tiny details to make time look one way. The section closes by returning to a simple planetary scene, a cooling lava plain under an ancient sky, heat radiating upward, convection in the mantle below and above, space. Absorbing infrared photons without returning them. There is no reversal. The heat leaves. The rock cools. Crystals lock in. The arrow of time is felt as a one-directional settling, and that settling is the condition for everything else. Oceans, atmospheres, biology to become stable enough to persist. Simulation theory remains here as a quiet interpretive temptation. The world feels like it has. An update rule entropy increases gradients, dissipate structures, emerge when energy flows. But the narrative does not claim an external programmer. It leaves the deepest question where it belongs, unresolved and calm. Why the universe begins with an arrow already possible, why time's direction is so reliable, and why Earth's long cooling feels like a slow irreversible settling into the only kind of stillness that allows complexity to exist at all. Heat continues to leave the planet, and in its leaving it creates room for rhythm. The narrative follows the first large, repeatable rhythm that becomes easy to feel even across deep time, the coupling of Earth and Moon, a gravitational duet that is not sentimental, only mechanical, and yet it leaves patterns on shortcut lines and in the length of the day. The accepted fact is that tides arise because gravity varies with distance stretching Earth slightly toward and away from the Moon, and that tidal friction dissipates energy, slowing Earth's rotation and causing the Moon to recede over time. This is not speculation. Lunar laser ranging measures the Moon's present recession rate in centimeters per year on average, and geologic and paleontological records support longer-term changes in day length. Only took a nearby satellite to make timekeeping a little less arbitrary. The narrative stays soft and looks at water first because the ocean is where the tide is visible. A tide is an energy transfer, a steady conversion of orbital and rotational energy into heat through friction in moving water and flexing rock. Coastlines experience the rise and fall, and in the early Earth this motion can be stronger when the Moon is closer, though the exact magnitude depends on ocean basin geometry and dissipation factors that vary with continental arrangement and depth. Uncertainty remains in reconstructing ancient tidal amplitudes precisely because the oceans change shape, the continents drift, and the seafloor rises and falls. Yet the direction of evolution Moon moving outward, day lengthening, is robust. Only took a few billion years for a day to stretch quietly from something shorter to something familiar. A lesser-known real-world detail rests in the existence of tidal rhythmites, layered, sedimentary deposits that record tidal cycles. In certain environments, alternating layers of silt and clay accumulate in patterns influenced by daily tides, fortnightly spring neap cycles, and even longer cycles tied to lunar months. Some ancient rhythmites preserve counts that allow estimates of the number of days in a year, long ago implying shorter days in Earth's past. These layers are not cinematic, they are thin repetitive laminations in mudstone, as if the ocean keeps a metronome and writes it down. Only took a quiet estuary to archive astronomy and sediment. The narrative lets this detail become a gentle bridge between physics and information, because these rhythmites store a record of periodicity without any intention. They are physical memory created by repeated forcing. The simulation metaphor sometimes thrives on periodicity, clock cycles, refresh rates, ticks. Yet Earth's tides are not synchronized to an external clock. They are consequences of gravity and angular momentum, and their periods vary gradually as the system evolves. The resemblance to ticks is a resemblance only. Still, the mind notices that the world is full of cycles that can be counted. Only took repetition to make reality feel countable. The ironies arrive softly dry and unforced. The first irony is that tides which seem like gentle shoreline motion are the manifestation of energy loss. Earth's rotation is literally being spent slowly as heat. The second irony is that the Moon, which looks like a symbol of stillness, is actually migrating, and its distance is a historical variable. The third irony is that humans measure time by days and months, while the lengths of those units are themselves moving targets on geological timescales. Only took a planet to make its own calendar unstable. The narrative remains grounded and turns to the Moon itself, not as a mythic object but as a physical record. The lunar surface preserves impacts and ancient solar system history with less recycling than Earth, because there is no plate tectonics and very limited erosion. This is accepted. The Moon is a more stable archive of early bombardment, though interpreting crater populations and absolute ages requires calibration from radiometric dates of returned samples. Uncertainty persists in translating crater counts into precise impact flux histories, especially for the earliest times. Some models suggest a spike in impacts. Others suggest a declining flux without a sharp spike. The lunar record is invaluable, but it is not a simple calendar. Only took a cratered surface to preserve history and still leave room for disagreement. The narrative brings the focus back to Earth's rotation, because rotation shapes climate and ocean circulation too. A faster spinning early Earth has stronger Coriolis effects, potentially influencing atmospheric circulation patterns and ocean gyres. Yet the precise climatic outcomes depend on many factors: continental positions, greenhouse gas levels, solar luminosity, and the uncertainty in reconstructing early climates remain substantial. The point is not to predict the exact weather of the Archean. It is to notice that the day's length is a boundary condition for fluid dynamics. A gentle modern analogy can hover like stirring a cup. More quickly changes the swirls, a faster rotation changes, planetary scale circulation, though the analogy stays quiet and incomplete because the planet is not a cup. Only took rotation rate to shift the geometry of moving air and water. The narrative now threads in the section's deeper theme emergent patterns. The laws governing gravity are simple in expression compared to the complexity of the outcomes. A two-body problem is solvable. Add a third body and behavior can become chaotic in certain regimes. Earth-Moon-Sun interactions create complex tidal patterns, precession, and long-term variations. The accepted fact is that gravitational systems can exhibit sensitive dependence on initial conditions, and that even with deterministic laws, long-term prediction can be limited. This is well known in celestial mechanics and dynamical systems. Here lies the section's quiet mystery. Why do simple laws generate rich complexity? And why does the universe so often sit near regimes where structure, pattern, and variability coexist? Simulation theory sometimes interprets this as designed complexity, but physics explains it as nonlinear dynamics and feedbacks. Still, the deeper why these laws question remains, and the narrative leaves it open. Only took a simple inverse square law to create tides, eclipses, and chaotic resonances. The story keeps the Earth-Moon system as a steady, slow machine converting motion into heat. Tidal friction warms the oceans, and the solid Earth slightly contributing a small but real heat flux. Over time, the dissipation changes, and in some periods resonance between ocean basins and tidal forcing can amplify tides, increasing dissipation and altering the rate of lunar recession. There is uncertainty here because ancient ocean basin geometries are not perfectly known, and resonance effects can be significant. The planet's history is therefore not a smooth curve, but a curve with changing slope influenced by geography. Only took continents moving to change how quickly the moon drifts away. A lesser-known detail rests in the way biology later records day length too. Certain fossils, like some corals and bivalves, show growth bands that can be daily and seasonal, allowing estimates of days per year in the distant past. These are younger than the earliest eons, but they reinforce the principle that Earth's rotation rate changes. The narrative does not lean on them heavily. It simply notes that multiple archives converge. Only took a living organism laying down bands to become a clock for astronomy. The simulation metaphor returns gently, because cyclicity and periodicity can feel like computational updates. Yet the narrative insists on the groundedness tides are not pixels refreshing. They are water responding to gravity. The moon's recession is not an intentional parameter change, it is angular momentum exchange under friction. And yet the world's ability to store these cycles in sediments to let them be read later is striking. It feels like information, like a log file written by nature. The quiet uncertainty becomes philosophical again without leaving science. Is the universe best understood as matter and energy, or as information and computation, or are these simply different languages for the same underlying reality? Only took two valid descriptions to make certainty about fundamentals elusive. The section ends with a calm shoreline scene that holds both scales at once. Waves move in and out under lunar pool sediments, settle in thin laminate, and somewhere beneath the crust rock flexes minutely with each tide. Above the moon continues its orbit, and Earth continues its spin, both slowly changing, both obeying the same laws. The rhythm is real, countable, archived. It is a reminder that reality can look like a system running on cycles while being at the same time a physical world of water, stone, and gravity. The narrative leaves the question open, allowing the tide to rise and fall without needing to decide whether it is an update in a program or simply the oldest kind of motion mass responding to mass across distance, creating pattern without intention and writing it quietly into mud. The ocean remains the planet's widest moving surface, and it organizes itself without instructions simply because water gravity, rotation, and heat cannot help but make patterns when they meet. The accepted fact is that ocean circulation is driven by differences in density, set by temperature and salinity, together with winds and Earth's rotation producing currents that transport heat and dissolved chemicals across basins. Even on a young Earth with different continents and an anoxic sky, the same physical principle applies. Warm water tends to be lighter, cold water heavier, salty water denser, fresh water lighter, and the planet's spin bends moving flows into curved paths through the Coriolis effect. The narrative lingers on this as a kind of planetary sorting that resembles intelligence only because it is consistent. Only took water being heavier when cold to invent a global conveyor that no one can see from the shore. As Earth cools enough for persistent oceans, the sea becomes not just a reservoir, but a mediator between interior and atmosphere. Hydrothermal systems inject heat and reduced chemicals from the crust into seawater. Volcanic gases dissolve and react. Rain and rivers deliver ions weathered from rock. In an anoxic world, seawater chemistry differs in significant ways from modern oceans. Ferrous iron can remain more soluble. Sulfur can circulate in different forms, and the redox boundary between surface and depth behaves differently because oxygen is scarce. This is consistent with geochemical proxies and the later appearance of iron-rich sedimentary deposits. Yet even without oxygen, the ocean does not sit as a uniform broth. Temperature gradients form between equator and pole, between surface and depth, between regions warmed by sunlight and regions cooled by upwelling. Salinity gradients arise from evaporation and rainfall, from freezing and melting from restricted basins. Currents begin, and once they begin, they shape everything. They touch climate, chemistry, sedimentation by moving heat and matter. A lesser-known detail rests in the way the ocean can stratify into layers that barely mix for long periods, especially when surface waters are warmed and freshened, while deeper waters remain cold and salty. Such stratification can create a quiet separation of worlds, a sunlit upper layer exchanging with air, and a dark, deep layer exchanging with rock. In later Earth history, this stratification can preserve anoxia at depth, even when the surface becomes oxygenated, and in early Earth it can help maintain distinct chemical reservoirs. Only took a thin density difference to keep waters from mixing for centuries, as if the ocean prefers privacy. The narrative keeps the title's philosophical theme at the edge, by noticing that these layered reservoirs behave like storage. They hold information in concentrations and gradients. A gradient is not a thought, but it is a difference that can do work. In physics, free energy is the ability of a system to produce change, and gradients are where that ability lives. The ocean becomes a vast library of gradients, pH differences near vents, redox differences between reduced hydrothermal fluids and more oxidized surface waters. Salinity contrasts temperature steps. The accepted fact is that chemical gradients can drive reactions, and that living systems later harness such gradients, especially proton gradients, across membranes to power metabolism. But even before life gradients exist as a consequence of geochemistry and circulation, the quiet scientific mystery here is how Information like order emerges from these gradients without assuming a designer, how complex structured chemical networks arise naturally, and where the boundary lies between mere chemistry and chemistry that begins to persist and copy. This is not a solved problem, and it is not only about biology, it is about how physical systems generate and maintain non-random structure under energy flow. Only took energy moving downhill to make patterns look uphill. The ocean's organization also produces visible signatures. Where currents meet, they create fronts. Where deep water rises, it brings nutrients and dissolved chemicals to the surface. Where surface water sinks, it carries surface chemistry into the deep. In a world with microbial life beginning to copy itself, these circulation patterns become ecological architecture, determining where energy and nutrients concentrate. Yet the narrative stays in process rather than story. It notes that the ocean is a mixer and a separator at once. Depending on scale, it stirs basins and also maintains layers. It spreads heat and also preserves cold depths. It distributes chemicals and also allows localized extremes near vents and shallow shelves. A gentle modern analogy can hover like a slow planetary breathing, with upwelling as exhale and sinking as inhale, except the breath is driven by density and wind, not intention. Only took water responding to sunlight and cold to imitate respiration in motion. The ironies arrive softly dry and sleepy without turning into humour. The first irony is that the ocean looks like a featureless surface from space, yet it contains more structured layering and circulation than most landscapes on land. The second irony is that water is often imagined as a symbol of softness, yet its moving mass is one of the strongest shapers of climate and geology, able to carve continents, dissolve mountains, and transport heat across the planet. The third irony is that the ocean's most important work storing heat-mixing salts carrying chemical gradients happens in darkness far below the surface where most attention naturally goes. Only took a sunlit surface to distract from the deep machinery. The narrative slows into a specific physical process that reveals how order forms in water, the creation of thermohaline circulation. Surface waters in some regions cool, become denser and sink, drawing in other waters to replace them. In modern Earth, this happens notably in the North Atlantic and around Antarctica, but on ancient Earth the geography is different, and the exact sinking regions may shift. Still, the principle is universal. Dense water sinks, and because it sinks it must be replaced, creating flow. This circulation can operate on timescales of centuries to millennia, a slow turnover that smooths some differences while preserving others. The uncertainty is how this circulation behaves under early Earth boundary conditions. Different continental arrangements, perhaps different salinity patterns, different atmospheric compositions, different heat flux from the interior. Models can explore scenarios, but the rock record provides only indirect constraints. Only took missing ocean basins from 4 billion years ago to keep ancient circulation mostly hypothetical. The narrative holds another lesser-known detail in the chemistry of the sea itself. The ocean's composition is not fixed, and over geological time, it can shift between calcite seas and aragonite seas, reflecting changes in the magnesium to calcium ratio of seawater driven by seafloor spreading rates and hydrothermal exchange. This concept is better documented for later Phanerozoic time, but it hints at a deeper truth: hydrothermal circulation through basaltic crust can significantly alter seawater chemistry by exchanging ions and heat. On early Earth, with higher heat flow and a more active seafloor volcanism, hydrothermal exchange may be even more influential, potentially making seawater chemistry markedly different from today in ways that are still not fully reconstructible. Only took seawater percolating through hot rock to rewrite the ocean's recipe. The quiet mystery becomes sharper here. If the ocean's chemistry is so sensitive to deep processes, how confidently can any single early ocean composition be asserted? Proxy records are sparse and altered. Ancient seawater does not remain bottled. It is inferred through mineral assemblages, isotopic systems, and sedimentary patterns, each with assumptions. The narrative does not make the ocean unknowable, it simply acknowledges that some aspects remain uncertain. The sea is real, but its earliest exact salt balance is not fully recoverable. Only took billions of years of circulation to erase the original mix. The section remains gently tethered to the project's theme by noticing that in both physics and earth science, the world is often reconstructed from partial data signals in spectra ratios in isotopes, laminae, and sediment. In the ocean, signals are gradients and cycles. Some of those cycles become archives. Tidal rhythmites already hold lunar periodicity. Varves in certain lakes and basins later record seasonal layering. Chemical bands in marine sediments record redox and productivity cycles. Even without choosing the simulation metaphor, the ocean behaves like a system that stores and releases information in patterns. It is a physical memory, not a conscious one. Yet the deeper question remains open: why a universe governed by simple laws produces systems that so readily generate readable structure, from spiral galaxies to spiral crystal growth to layered seas. Only took one planet's ocean to look like a pattern generator. The narrative ends by letting the ocean become a quiet, stable presence again, even though it is never still. The surface reflects light and loses heat at night. Beneath, currents slide along invisible density surfaces. Along the seafloor, hydrothermal fluids rise and spread, carrying reduced compounds that react, precipitate, and alter the water's chemistry. Salts remain dissolved and temperature remains uneven, and that unevenness keeps the sea alive with motion. No verdict is offered about simulation or non-simulation. The ocean simply continues to organize itself because the laws of fluids and heat are what they are, and because gradients exist and must relax, and because Earth's rotation shapes relaxation into spirals and jets. In that lawful motion, the planet carries a quiet kind of order that can be described, measured, and still not fully reduced to a single satisfying explanation of why order appears so easily. The water moves, stores, mixes, separates, and repeats, and the narrative rests with that repetition, letting the sea's organized restlessness become a calm proof of reality's strange talent to behave like a system that remembers, while being nothing more mystical than water, responding to physics across deep time. The ocean's motion continues, but beneath it the planet's deeper motion begins to matter more because Earth's surface is not a fixed shell. It is a skin that is repeatedly made and unmade, and the making and unmaking is one of the clearest ways reality behaves like a system with rules and memory limits. The accepted fact is that Earth's lithosphere is broken into moving plates whose motion is driven by mantle convection and gravitational forces such as slab pull and ridge push, and that plate tectonics recycles crust through seafloor, spreading subduction and continental collision. This is supported by modern measurements of plate motion, by the distribution of earthquakes and volcanoes, by the age pattern of oceanic crust, and by the geological record of mountain belts and ancient ocean basins. Only took a planet with internal heat to keep rearranging its own surface for billions of years, as if permanence is not part of the design. The narrative stays slow and lets plate tectonics be seen not as drama but as a quiet conveyor, a long set of motions measured in centimeters per year, too slow to feel yet relentless enough to erase oceans and raise continents. New oceanic crust forms at mid-ocean ridges where mantle melts and basalt rises, solidifies and spreads outward. Old oceanic crust cools, thickens, becomes denser, and eventually sinks at subduction zones, carrying water and altered minerals down into the mantle. Continents, being more buoyant, resist subduction and survive longer, accumulating, colliding and thickening into mountain belts. The surface thus behaves like an editor. It writes new basalt, then deletes it. It stitches fragments, then tears them apart. A lesser-known real-world detail rests in the way seafloor spreading literally carries magnetic stripes as basalt cools at ridges. Magnetic minerals like magnetite align with Earth's magnetic field, recording its polarity. Because the field reverses through time, the ocean floor becomes a barcode of alternating magnetic polarity bands, symmetric about ridges, a pattern that helped confirm plate tectonics in the 20th century. Only took iron minerals, freezing in basalt, to turn the seafloor into a tape recorder for invisible fields. The narrative lingers on that because it feels like stored information without an author, a physical process leaving a readable trace later decoded. This is the quiet similarity that sometimes draws minds towards simulation language. Yet the trace does not imply an external programmer. It implies only that the laws are consistent and that materials can preserve states. Still, a quiet scientific mystery sits close to the center of the section. When does plate tectonics begin in Earth's history, and what form does it take early on? The modern plate system is well understood, but the Hadean and early Archean record is sparse and heavily reworked. Some evidence suggests early subduction-like processes. Other interpretations support a more stagnant lid regime punctuated by episodic overturns, with plate-like behavior emerging gradually rather than appearing fully formed. The onset timing remains debated, and because early rocks are rare and altered, the argument is slow and careful. Only took the planet recycling its oldest crust to make the start date of its recycling uncertain. The narrative remains grounded by moving into the mechanics of plates without repeating basic explanations already introduced elsewhere. Water introduced earlier as ocean and hydrothermal agent reappears here as a deep weakening influence. Hydrated minerals and fluids in subduction zones can lower melting temperatures and reduce rock strength, helping slabs bend and descend. This coupling between surface water and deep tectonics is accepted in broad outline. It suggests that oceans do not merely sit on the planet, they participate in how the surface breaks and moves. A gentle modern analogy can hover restrained like a small amount of moisture changing how clay yields under pressure. Water in rock changes how lithosphere deforms. Only took a few weight % of water locked in minerals to influence a planet's mechanical style. The narrative then turns toward continental crust because continents are a kind of long-lived memory device in geology. Oceanic crust is young, almost all of it is less than about 200 million years old today because it is continually recycled. Continental crust can survive for billions of years in cratons, the stable cores of continents. This difference is accepted and measurable. It means the planet's memory is uneven. One part is constantly overwritten, another part preserves fragments. A poetic detail appears in the oldest continental regions where rocks can contain zircons older than the rocks themselves, crystals recycled into younger sediments, and metamorphic terrains like words cut from older pages and pasted into newer ones. Only took a crystal's stubbornness to carry a sentence across vanished landscapes. The narrative lets this become a quiet theme. Tectonics creates both erasure and preservation, and the balance between them is what makes deep time readable at all. The ironies arrive softly dry and sleepy without any spike in tone. The first irony is that Earth is the only known planet with active plate tectonics today, and it is also the planet that most aggressively destroys its earliest evidence as if it is designed to forget. The second irony is that the seafloor which covers most of the planet is geologically young, while the oldest rocks sit as small islands of endurance on continents. The third irony is that humanity's most confident reconstructions of deep Earth history depend on a process that constantly hides its own beginnings. Only took a moving planet to make its own origin story hard to read. The narrative now lingers on subduction as a deep exchange between surface and interior. At subduction zones, slabs carry altered basalt sediments and water downward. Some of this material is released through dehydration reaction fueling arc volcanism and returning volatiles to the surface. Some may descend deeper, contributing to mantle heterogeneity and long-term cycling of elements like carbon, sulfur, and water. This is accepted geochemistry. The mantle is not perfectly mixed. It carries isotopic signatures suggesting long-lived reservoirs and recycled components. Yet uncertainty remains about rates and depths, how much carbon is subducted and stored versus returned, how much water reaches the deep mantle, how efficiently slabs penetrate to the lower mantle or stall, and how these processes vary through time. Only took a slab's fate in the mantle to influence climate on the surface slowly and indirectly. The narrative holds this as a quiet mystery of coupling the surface and the deep interior are not separate systems, but the exact pathways of exchange are partially hidden. Even today, imaging slabs in the mantle relies on seismic tomography, a method that infers structure from wave speed variations, similar in spirit to how early time is inferred from isotopes. The world is read by signals rather than by direct sight. A lesser-known detail rests in the existence of ultra-high pressure minerals found in some metamorphic rocks, minerals like coesite or even microdiamonds that indicate rocks have been buried to great depths and then returned to the surface. These minerals are evidence that parts of the crust can take deep journeys and come back carrying pressure memories locked into crystal structure. Only took a silica polymorph to confess that stone has been far below any mountain. The narrative keeps that detail quiet, not dramatic, because it is simply another way the planet writes logs into matter. Now the section touches the question of habitability, because plate tectonics is often linked to long-term climate regulation through the carbon cycle. Weathering of silicate rocks draws down CO2 while volcanism returns CO2 to the atmosphere. Over long timescales, this negative feedback can help stabilize climate. This is an accepted framework, though. Its strength and details depend on many factors, and other mechanisms can also regulate climate. The quiet scientific mystery here is why Earth maintains liquid water for so long, while Venus becomes hotter and Mars becomes colder and drier. Plate tectonics may be part of the answer, but it's not the only factor. Initial conditions. Size distance from the Sun, atmospheric evolution, and internal heat all matter. The narrative does not claim a single cause. It holds the uncertainty Earth's long habitability emerges from multiple coupled processes, and the exact balance remains a field of research. Only took a narrow range of conditions for a planet to keep oceans for billions of years, and the reasons still do not reduce to one sentence. The simulation theme remains at the edge because plate tectonics looks like an algorithm that overwrites a surface while preserving a few registers. Cratons, isotopic reservoirs, mineral inclusions like data stored at different levels of volatility. Yet the narrative remains scientifically grounded. This is how physical systems behave when they have energy flow phase transitions and buoyancy-driven motion. Overwriting is not a design choice. It is a consequence of convection and density. The deeper question stays philosophical and unresolved. Why the laws allow such a rich middle state where the surface is neither frozen in place nor entirely melted, but mobile enough to cycle, stable enough to archive. Only took a planet not too hot and not too cold to keep rewriting itself. The section ends with a slow image that holds both erasure and memory. A mid-ocean ridge quietly extruding basalt into seawater pillow lavas forming in darkness. A trench swallowing old crust sediments folding and descending. An arc volcano releasing gases that once came from the mantle and will later dissolve into oceans again. a craton sitting far inland holding ancient minerals that remember different skies. Above the atmosphere moves and reigns, and below the mantle convex indifferent and patient. Reality in this view behaves like a system that runs on rules and cycles with buffers and resets and slow drift, yet it remains undeniably material stone deforming minerals, transforming heat escaping. The narrative does not decide whether this resembles computation because it is computed, or because computation is the best metaphor humans have for lawful complexity. It simply rests with the planet's most honest habit to move slowly, to recycle relentlessly, and to leave just enough stubborn evidence behind that the movement can be known even if its first beginning remains quietly out of reach. The moving plates and the moving ocean share the same surface, and above them, the atmosphere becomes the planet's most immediate interface with light. The narrative remains whisper soft and returns to the idea that reality announces itself through signals because the sky is not only air, it is a filter and a signature. The accepted fact is that gases absorb and emit light at specific wavelengths because molecules have quantized vibrational and rotational energy levels, creating spectral fingerprints. Water vapor, carbon dioxide, methane, ozone each leaves a distinct pattern in infrared or ultraviolet spectra. And these patterns are measured in laboratories and observed in atmospheres across the solar system and beyond. Spectroscopy is one of the strongest tools in modern science. It connects the smallest quantized transitions to the largest scales of planets and stars. Only took molecules vibrating to make air readable from a distance. The narrative lingers on the way this applies to Earth. Earth's atmosphere regulates surface temperature through the greenhouse effect. Certain gases absorb outgoing infrared radiation and re-radiate it, warming the lower atmosphere and surface compared to an airless planet at the same distance from the Sun. This is accepted physics quantified in radiative transfer models and supported by observations. The exact composition of Earth's atmosphere changes through time: anoxic early skies, later oxygenation varying CO2 and methane, yet the principle remains. Light arrives mostly in visible wavelengths from the Sun, and Earth emits mostly infrared. The atmosphere mediates that exchange. A lesser-known real-world detail rests in the concept of pressure. Broadening spectral lines are not infinitely sharp in real atmospheres. Collisions between molecules broaden absorption features, meaning that atmospheric pressure and composition affect how strongly gases absorb across bands. This is one reason why thick atmospheres can trap heat differently than thin ones, even with similar gas fractions. Only took molecules bumping into each other to change a planet's temperature. The narrative stays calm and notes a quiet scientific mystery that sits at the boundary of physics and philosophy. Why is the universe so mathematically compressible? Spectral behavior can be written in equation line lists, radiative transfer codes. The sky becomes a problem of computation, and yet the computation predicts reality with stunning accuracy. This does not imply simulation. It implies that nature follows consistent patterns that mathematics can capture. But the deeper why remains open. Why do abstract mathematical structures map so well onto physical behavior? It is a question that has lingered for centuries, sometimes called the unreasonable effectiveness of mathematics. Only took a few symbols on paper to match a sky full of molecules. The narrative returns to Earth's sky as an evolving boundary condition. In early Earth, with low oxygen, ultraviolet light penetrates deeper, and photochemistry can produce hazes. Later, as oxygen rises, ozone forms in the stratosphere, absorbing ultraviolet and reshaping surface radiation environments. This is accepted in outline ozone formation, depends on oxygen availability and ozone changes, UV flux. The timing and exact oxygen thresholds for robust ozone are debated, and local oxygen oases complicate the transition. The uncertainty remains: how quickly does UV shielding develop, and how does that affect surface chemistry and biology? Only took a thin layer of ozone to change what sunlight can do to molecules on the ground. The ironies arrive softly dry and sleepy. The first irony is that the atmosphere is mostly invisible, yet it controls habitability more decisively than most visible landscapes. The second irony is that the sky's most important features are lines in a spectrum, numbers on a graph, because human eyes are tuned to a narrow band of light. The third irony is that a planet's climate can be changed by trace gases measured in parts per million, as if the largest system responds to the smallest tweaks. Only took a few molecules per million to tip oceans toward ice or warmth. The narrative lingers on light itself because light is the messenger that makes distant knowledge possible. James Webb. Though not the focus here, is an example of how infrared light carries information from distant galaxies. On Earth, infrared light carries information from the surface and atmosphere, and satellites read it to infer temperature, humidity clouds, and composition. Even without mentioning satellites explicitly, the principle stands: the planet emits, and the emission encodes the state of the emitter. This is a physical relationship, Planck's law radiative transfer, not a philosophical metaphor. Yet it brushes again against the simulation theme. Information is not an add-on. It is inherent in physical processes. The quiet uncertainty becomes: is information merely what observers extract, or is it something the universe has independent of observation? Physics uses both language depending on context. Only took measurement to make information feel both real and slippery. The narrative returns to Earth's history as a sequence of atmospheric states that can be inferred from proxies because direct samples do not survive for most of deep time. Bubbles trapped in ice cores reveal recent atmospheres, but beyond that, scientists rely on chemical signals in rocks, isotopic ratios, mineral oxidation states, sulfur signatures, organic biomarkers, paleosols. These are indirect. They require interpretation. The accepted fact is that such proxies can constrain past atmospheric composition, but uncertainties remain sometimes large. The quiet mystery here is methodological: how to reconstruct ancient atmospheres with confidence when the record is incomplete and altered. Only took time to turn air into an inference problem. A lesser-known detail rests in the way raindrops themselves can leave a record. In rare cases, fossilized raindrop imprints in ancient sediments have been used to estimate ancient air density, though such interpretations are challenging and debated. The idea is simple: raindrop terminal velocity depends on air density, and imprint sizes might preserve hints. But erosion sediment properties and impact angles complicate the method, and the results are not definitive. Still, it is a poetic, real-world attempt to read the weight of ancient air from the mark of falling water. Only took a raindrop hitting mud to tempt a measurement across billions of years. The narrative holds that as a gentle reminder that Earth's atmosphere is both present and elusive in deep time. Now the story touches the mathematical side again without leaving calm. Spectra, climate, and chemistry are governed by equations, yet climate in particular exhibits nonlinear feedbacks. Clouds can cool or warm depending on type and altitude. Ice reflects light. Greenhouse gases warm. Aerosols scatter and absorb. Ocean circulation redistributes heat. Even with known laws, predicting the exact behavior of a coupled climate system can be difficult, especially under different ancient boundary conditions. This is accepted in complexity. Science deterministic systems can be sensitive and produce emergent behavior. The quiet mystery is not whether physics is lawful, but why prediction is limited in practice, and whether that limitation is purely computational or partly fundamental. Simulation theory sometimes interprets unpredictability as a feature of an underlying computation. Physics interprets it as chaos, complexity, and incomplete knowledge of initial conditions. The narrative holds both interpretations as languages, not verdicts. Only took a few feedback loops to make certainty expensive. The section keeps the imagery elemental. A dawn breaks over a basalt plain. Light enters the atmosphere and scatters. Molecules absorb certain wavelengths and let others pass. The sky's colour depends on scattering. The warmth depends on absorption. The water cycle depends on energy flow. Clouds form when air cools and water condenses, reflecting sunlight and trapping infrared. Rain falls carrying dissolved gases to the ocean and to rock. In this quiet loop, the planet's atmosphere acts like a membrane mediating exchange and regulating stability. It is not a screen, it is a reactive layer of gas, governed by collisions, quantum transitions and gravity. The narrative still leaves room for the deeper philosophical uncertainty, why the laws are so precise and so expressible, why the constants allow stable molecules, why mathematics fits. These questions remain open without requiring a simulation hypothesis, and yet they are the kind of questions that keep simulation theory from being easily dismissed by some minds, not because evidence points to it directly, but because the world's describability and discreteness invite metaphors of computation. Only took a universe that can be modelled to make metaphors feel tempting. The section ends with the sky becoming quiet again, not because it stops moving, but because it continues in its steady way, gases drifting spectral lines waiting to be read, sunlight arriving, infrared leaving. The atmosphere remains an interface where information is carried by photons, where chemistry shapes habitability, and where Earth's history is partly hidden and partly encoded. In that thin layer, reality shows both its consistency and its mystery, predictable enough to be described, complex enough to remain partly uncertain, and always present as the softest of Earth's physical layers, holding light like a delicate instrument that never stops playing. The atmosphere's spectral lines and the ocean's layered gradients remain in motion, and within that motion something begins to persist in a new way, not as a stable mineral lattice or a repeating tide, but as chemistry that makes more of itself. The accepted fact is that life exists on Earth by at least about 3.5 billion years ago, supported by multiple lines of evidence, including stromatolite-like structures in ancient rocks and isotopic signatures consistent with biological carbon fixation. The planet does not need a narrative for this. It only needs liquid water, chemical gradients, and time, and it has all three. Only took a few 100 million years after oceans settle for chemistry to begin copying itself, which is both remarkably fast and endlessly slow depending on the scale being used. The narrative remains whisper-soft and stays grounded in real settings where early life is most plausibly housed shallow marine shelves with microbial mats and deep seafloor environments where hydrothermal systems feed reduced compounds into seawater. Hydrothermal circulation is an accepted process on any planet with water, and a hot rocky crust seawater percolates into fractured basalt, heats, reacts and emerges, altered, carrying dissolved metals, hydrogen sulfide and other species. These flows create gradients, differences in temperature, pH and redox state that can drive chemical reactions. The story lingers on a single vent field as an elemental scene. Dark water mineral chimneys, fluids, rising precipitates forming as hot and cold mix. It's not dramatic, it's continuous like a slow fountain. A lesser-known, real-world detail rests in the microstructure of some hydrothermal chimneys. Precipitation can build porous mineral walls with tiny compartments and channels forming natural labyrinths where molecules can become concentrated. These pores are not invented. They are a consequence of mineral growth and fluid flow, and they can create microenvironments with steep gradients over millimeter distances. Only took stone precipitating in seawater to build tiny rooms before cells ever build membranes. The narrative holds that detail gently because it shows how information like order, localized structure that matters, can arise without intention. Yet the central quiet scientific mystery remains the origin of life as a specific pathway is still not fully explained. It is not a gap that can be filled by one poetic guess, and the narrative refuses to fill it with fiction. The uncertainty is precise. How does non-living chemistry cross the threshold into systems that both metabolize and replicate with heredity? And how do those systems become enclosed, robust, and evolvable? Many hypotheses exist. Metabolism-first scenarios in vents, replication-first scenarios involving nucleic acid-like polymers, wet-dry cycling in surface pools, catalytic mineral surfaces, but no single pathway has been confirmed as the historical route. Only took decades of careful experiments to show that plausible steps exist and still not to reveal which steps actually happened first. The narrative stays with what is accepted in broad outline. Life's core features include replication with variation metabolism that channels energy through chemical networks and compartmentalization that separates inside from outside. In modern organisms, these are intertwined, but their earliest coupling is unknown. The planet's chemistry provides raw materials: carbon dioxide dissolved in seawater, nitrogen compounds in limited forms, phosphorus in minerals, sulfur species from volcanism and hydrothermal reactions, ion cycling between oxidation states depending on oxygen availability. In an anoxic world, ferrous iron is more abundant in solution, and reduced gases can persist longer. This chemical landscape is different from the modern surface world, and it matters for what kinds of reactions are favoured. The narrative holds an image of the Archean Ocean as faintly tinted in places by dissolved iron and suspended particles, the water carrying chemistry as quietly as it carries heat. Only took iron staying soluble to make the sea a different colour long before algae paint it green. The story then moves toward replication as a physical act. In molecular terms, copying requires templates, monomers, and conditions that favour polymerization over degradation. Laboratory work shows that nucleotides and amino acids can form under plausible prebiotic conditions, and that certain mineral surfaces can catalyze polymerization, while wet-dry cycles can concentrate solutes and drive condensation reactions. These are accepted as plausible mechanisms, yet the uncertainty remains about how robust, long and information-rich early polymers are, and how they avoid being diluted and hydrolyzed in bulk seawater. This leads to another quiet mystery that is both scientific and conceptual: the origin of biological information. How does the sequence become meaningful in the sense that it encodes function? And how does selection begin acting on sequence variation? The narrative does not pretend to solve it. It simply notes that once replication exists, selection becomes possible, and once selection exists, complexity can accumulate. Only took copying with errors to turn chemistry into history. The ironies arrive as softly as required, with no change in emotional slope. The first irony is that life's first great innovation is not strength or speed, but repetition making another copy, and then another with tiny differences. The second irony is that the planet's earliest life likely thrived without oxygen in conditions that would be lethal to many modern organisms, and yet it becomes the foundation for a later oxygen-rich world. The third irony settles like silt: the most consequential transformation on Earth begins at a scale too small to be seen unaided, and it leaves evidence so subtle that it takes billions of years and sophisticated instruments to infer it. Only took a microbe to transform a planet and leave almost no direct witnesses. The narrative remains in the Archean setting and approaches evidence with care. Carbon isotopes provide one of the most discussed signals. Many biological pathways favour carbon-12 over carbon-13, producing organic matter that is isotopically lighter than inorganic carbon reservoirs. In some ancient rocks, carbon isotope ratios are consistent with biological fractionation. This is widely used evidence, though. The story keeps the nuance certain. Abiotic processes can also fractionate carbon under particular conditions, and metamorphism can alter signatures, so interpretation requires context. The uncertainty is not whether fractionation exists, but how unambiguous the oldest signals are. Only took a few parts per thousand difference in isotope ratios to sustain a conversation that spans generations of geochemists. Another line of evidence appears in stromatolites' layered structures formed by microbial communities trapping sediments and precipitating minerals. Some Archean stromatolites are widely accepted as biogenic, and their layered textures show incremental growth in shallow waters. A lesser-known detail rests in how microbial mats can induce carbonate precipitation by changing local chemistry, altering pH and alkalinity through metabolism, so that stone forms in place around living films. This is not a metaphor. It is a real mechanism in many modern microbialite systems and is used to interpret ancient analogues. Only took microbes changing local water chemistry to make rock grow around them quietly, layer by layer. Yet even here uncertainty remains, though some layered structures can form abiotically, and the further back in time, the more alteration complicates interpretation. The narrative stays level, and accepts that the early record is sparse and contested in places, while life's early presence is still the most parsimonious explanation for many features. The story then brings forward an idea central to the project's title without becoming speculative. The language of code and information is tempting in biology. DNA and RNA sequences carry heritable information in a way that can be described in bits, and cellular processes can be modeled as information processing. This is accepted as a useful framework in bioinformatics and theoretical biology. But usefulness does not determine ontology. A genome behaves like a code in the sense that sequences map to functions through cellular machinery, yet this mapping arises through evolution and chemistry, not necessarily through external authorship. The quiet mystery becomes philosophical and scientific at once. Why does biology's information-like behavior emerge so naturally from chemistry under selection, and where exactly does the line lie between metaphor and fundament? Only took evolution to make information feel literal in living matter. A gentle modern analogy can hover restrained like a recipe written in a language that the kitchen itself evolves. Early genetic systems may begin with crude ambiguous mappings that become more reliable over time. The analogy remains soft and incomplete because the earliest kitchen is a planet and the earliest recipe is chemistry. The narrative then returns to the physical constraints that shape early life. Energy is the constant currency. In hydrothermal systems, redox reactions such as hydrogen reacting with carbon dioxide can release energy, and mineral catalysts can facilitate pathways. In sunlit shallows, photochemistry can provide energy, though early photosynthesis may begin as anoxygenic forms that do not split water. Oxygenic photosynthesis is not introduced as a main actor yet here. It remains a later lever that will change the atmosphere. For now, the story holds early metabolisms as diverse and largely anaerobic, consistent with what is known about microbial physiology and early Earth conditions. Only took life to find multiple ways to move electrons, as if metabolism is a broad toolkit rather than a single invention. The section's quiet uncertainty widens again. Did life begin in the deep or in the shallow, in vents or in surface pools, or in more than one place with only one lineage surviving? The planet offers many laboratories. The record offers few definitive answers. The narrative does not dramatize the uncertainty. It lets it remain as an open space like a missing page that cannot be forced back into existence. Only took 4 billion years of recycling and alteration to make the most important beginning hard to locate. The narrative closes by returning to Earth's elemental motifs, Stonewater light dust now threaded with a new motif that is still material copying. In a porous chimney wall, molecules concentrate. On a mineral surface, a polymer grows by one unit. In a small compartment, a membrane-like boundary forms from amphiphilic molecules assembling spontaneously because their chemistry demands it. Somewhere in this long landscape of gradients and cycles, replication becomes stable enough to persist, and once it persists, the planet's history gains a new kind of memory, heritable variation. Reality continues to be lawful and physical, but now lawfulness produces entities that carry their own internal record sequences that can be compared, selected, and refined. The simulation idea remains here as a distant interpretive temptation. Life looks like code, and code looks like computation. Yet the narrative stays grounded in scholarly truth. Life's code is made of molecules, its copying is chemistry, and its origin remains unresolved in detail. The planet turns, the ocean circulates, and within the slow repetition of tides and currents, chemistry begins to remember itself. Life continues to copy in quiet water, and over time copying becomes not only persistence but influence, because metabolism does not merely use an environment, it changes it. The narrative remains even and slow and moves into the long chemical transition where oxygen, once rare and reactive, becomes increasingly present. The accepted fact is that Earth's atmosphere and oceans undergo a major rise in oxygen known as the Great Oxygenation Event, broadly placed around 2.4 to 2.0 billion years ago, evidenced by multiple independent proxies, including the disappearance of mass-independent fractionation of sulfur isotopes, changes in iron deposition, and the appearance of oxidized continental sediments. Oxygenic photosynthesis using light energy to split water and release oxygen is the ultimate source of this oxygen. The narrative does not turn this into triumph or catastrophe. It treats it as a geochemical reconfiguration. Only took microbes inventing a new way to use light for the sky to eventually change its composition. The story lingers on the time lag that makes oxygenation so quietly strange. Oxygenic photosynthesis likely begins well before oxygen accumulates globally, because oxygen is consumed by abundant sinks. Reduced volcanic gases react with oxygen. Dissolved ferrous iron in oceans reacts with oxygen. Reduced minerals encrust a mantle react with oxygen. For long spans, oxygen production is balanced by oxygen consumption, and the atmosphere remains largely anoxic even as oxygen is made in local places. This is accepted in broad outline. The quiet scientific mystery is why the balance tips when it does. What changes? Biological productivity and nutrient supply, tectonic style, volcanic gas, composition, burial of organic carbon, the oxidation state of the mantle, the rate of hydrogen escape to space. Many factors are studied, and no single factor fully explains all features without interacting with others. Only took a planet-sized set of sinks for oxygen to be made and spent again and again without ever building up. The narrative returns to the ocean because the ocean is where oxygen first meets the planet's largest chemical reservoir. In an anoxic seafarous iron can be abundant. When oxygen enters locally near photosynthetic mats, or more broadly, as oxygen increases, iron oxidizes and precipitates as iron oxides or other iron minerals. Banded iron formations become the most iconic record of this redox transition, alternating layers of iron-rich minerals and silica. Their existence and general association with changing redox conditions are widely accepted, though the exact mechanisms that produce rhythmic banding are still debated. A lesser-known detail rests in how some banded iron formations contain magnetite, an iron oxide that is magnetic, meaning ancient chemical precipitation can literally align with and respond to Earth's magnetic field later. when sampled adding another layer of signal to the stone. Only took oxygen reacting with iron to create rocks that can later point north. The narrative holds that quietly because it feels like the planet making new archives as it changes state. The ironies arrive softly dry and sleepy. The first irony is that oxygen, later essential for many complex organisms, begins as a toxic waste product to many early microbes, forcing evolution to invent defenses and alternative niches. The second irony is that the same oxygen that can destroy organic molecules also allows an ozone layer to form, which then protects organic molecules on land from ultraviolet radiation. The third irony settles: the atmosphere becomes breathable for creatures that do not yet exist, built by organisms that do not need that breath. Only took a few billion years of microbial labour to prepare a world for later lungs. The narrative remains grounded in evidence. Sulfur isotopes provide a particularly strong atmospheric marker. In a low-oxygen atmosphere, ultraviolet light can drive photochemical reactions that produce mass-independent fractionation, MIF signatures in sulfur isotopes, which are preserved in sedimentary rocks. When oxygen rises high enough to alter atmospheric chemistry and allow significant ozone formation, these MIF signatures disappear. The disappearance around 2.4 billion years ago is a key line of evidence for increased atmospheric oxygen. The narrative keeps the concept gentle. Sunlight writes a peculiar signature into sulfur when the sky is chemically permissive, and later oxygen changes the sky so the signature can no longer be written. Only took a different sky chemistry to change what sunlight can imprint on rock. Yet uncertainty remains in details. The exact oxygen thresholds involve the regional variability and the precise timing relative to other changes. The great oxygenation event is not necessarily a single step. It may involve pulses, overshoots, and stabilization phases. Proxy records suggest oxygen levels can fluctuate after the initial rise, and for much of the Proterozoic oxygen may remain below modern levels. The narrative holds this as a calm nuance. The planet does not flip a switch cleanly. It drifts, it oscillates, it settles. Only took Earth being Earth to make even a great event behave like a long transition. The story returns to methane because methane is one of oxygen's quiet casualties. In an anoxic world, methane can accumulate to higher levels because it is not rapidly oxidized. As oxygen rises, methane's atmospheric lifetime decreases and methane concentrations can fall. Because methane is a strong greenhouse gas, a reduction can cool the planet, potentially contributing to glaciations in the Paleoproterozoic. This linkage is discussed widely in the literature, though the magnitude, timing, and interplay with CO2 and other factors remain debated. The quiet scientific mystery is how tightly oxygenation and glaciation are coupled, and whether methane collapse is sufficient to drive global-scale cooling, or whether tectonic and weathering changes play dominant roles. Only took one gas becoming common to make another gas rare, and then the climate responds as if it notices. A gentle modern analogy can hover, like removing an insulating layer from a warm object. Reducing methane can let more heat escape, though the analogy remains soft because climate is not one layer, but a network of exchanges. The narrative then touches the deeper coupling between biosphere and geosphere. Oxygenation affects nutrient cycles. Oxidation changes the solubility and availability of metals like iron and trace nutrients like molybdenum, which can influence biological processes such as nitrogen fixation. Changes in nutrient availability can in turn influence productivity and organic carbon burial, which influences oxygen accumulation. This feedback network is complex, and while its components are understood, the full system behavior through time is still uncertain. Only took one element solubility changing to alter what life can do on a planetary scale. A lesser-known detail rests in the fact that some microbial metabolisms can use oxygen at extremely low concentrations, and that even small whiffs of oxygen can have outsized effects on chemistry. This means oxygenation may begin with subtle local impacts long before it becomes a global atmospheric condition. The narrative keeps this subtlety. The world can change through tiny concentrations acting as catalysts for new pathways, like small amounts of oxygen, enabling oxidative weathering that changes river chemistry, which changes ocean chemistry, which changes sedimentation. Only took parts per million to begin rewriting a planet's mineral inventory. The simulation theme returns gently because oxygenation looks like a system undergoing a state change, a kind of update that propagates through coupled subsystems. In computation metaphors, one might imagine a parameter crossing a threshold and triggering new behaviors. In earth science, this is understood as nonlinear feedbacks. Oxygen production increases, sinks, saturate or decline, thresholds are crossed, and a new stable regime emerges. The narrative remains grounded and neutral. The language of thresholds and regimes is common in complex systems science, and it does not require simulation to be true. Still, the deeper philosophical uncertainty remains. Why does reality so often organize into regimes and thresholds where small changes can lead to large shifts? Only took non-linear feedbacks to make history feel punctuated rather than smooth. The section ends with a calm image of Earth's surface being chemically repainted. Rivers carry oxidized products from continents. Oceans begin to lose some dissolved ferrous iron as it precipitates. Sulfur chemistry in the atmosphere changes. Ozone begins to form altering ultraviolet flux. Microbial life adapts, some retreating into anoxic niches, some evolving new aerobic metabolisms that harvest more energy from organic matter. The sky remains mostly nitrogen, still thin, still moving, but its trace composition becomes a different kind of interface with light. Oxygen, once a local molecule, becomes a global factor. Yet the narrative keeps one quiet gap open because it deserves to remain open. The precise chain of causes that tips Earth into oxygenation is still debated, and the world's complexity resists a single explanation. The planet does not explain itself. It only changes slowly and leaves behind proxies, sulfur signatures, iron layers, sediments that can be read, interpreted, argued over, and refined. In that reading, reality again resembles a system that logs its own state transitions, not because it is a simulation, but because physical processes once set in motion cannot help but leave traces of the paths they take. Oxygen's influence continues to spread through rock and water, and as it does, the planet's climate reveals another of its threshold behaviors, quiet at first, and then extensive ice advances far beyond the familiar. The narrative remains slow and even describing glaciation not as a spectacle, but as a change in reflectivity, a shift in how light is handled at the surface. The accepted fact is that Earth undergoes major glaciations long before recent ice ages, including Paleo-Proterozoic glaciations and later Neoproterozoic events, in which evidence suggests ice reaches very low latitudes. This evidence includes glacial deposits found in what paleomagnetic data and sedimentological context indicate are near equatorial settings, along with characteristic features such as dimectites and dropstones. Only took a few degrees of cooling repeated and reinforced for a planet to begin dressing itself in ice. The narrative begins with the physics that make such episodes possible. Ice is bright. It reflects a large fraction of incoming sunlight back to space. Dark ocean and dark rock absorb more sunlight. The accepted process is the ice albedo feedback. As ice expands, the planet reflects more sunlight, cooling further, allowing more ice to expand. This positive feedback can accelerate glaciation once certain thresholds are crossed. It is simple in principle and powerful in effect. Yet the planet is not a single surface. It is a coupled system of atmosphere, ocean and land, and the threshold is influenced by greenhouse gases, cloud behaviour, continental positions and ocean circulation. Only took light reflecting a little more to make temperature fall a little more, and then the process repeats as if it enjoys itself. The narrative holds the quiet scientific mystery that persists even within robust evidence. How fully does Earth freeze during its most extreme episodes? Some models favour a hard snowball state with near global ice cover and sealed oceans, while others favour a slush pool with persistent open water regions near the equator or seasonal openings that allow continued exchange. The rock record supports widespread glaciation and low-latitude ice, but it does not unambiguously dictate the exact global configuration. Paleomagnetic data carry uncertainties. Depositional environments can be complex. Later metamorphism can blur signals. The uncertainty remains precise. The extent, thickness, and continuity of sea ice during these events are still debated. Only took a few missing constraints to keep the planet's coldest geometry unsettled. The narrative lingers on a tangible real-world detail that anchors the cold in sediment dropstones. In certain fine-grained marine sediments, large isolated clasts appear surrounded by much smaller particles, interpreted as stones carried by ice, and released when ice melts falling through water to the sea floor. The image is quiet and literal. A stone slips from melting ice, sinks, lands, and is slowly buried. Later it is found embedded in ancient mudstone, a record of ice existing above water. Only took one rock falling into quiet mud to become a witness for ancient cold. The story remains cautious. Not every outsized clast is a dropstone, and alternative transport mechanisms must be considered. But in glacial contexts with other indicators, the interpretation is strong. The narrative stays with the carbon cycle next because ice does not advance and retreat by albedo alone. It is moderated by greenhouse gases, especially carbon dioxide. The accepted framework is that volcanic outgassing continues through glaciations, supplying CO2 to the atmosphere while silicate weathering. The major long-term sink for CO2 slows dramatically when continents are ice-covered and liquid water is limited. Over time, CO2 can accumulate, strengthening greenhouse warming until deglaciation occurs. This build-up then release mechanism is widely discussed for snowball Earth transitions, particularly in the Neoproterozoic. Only took volcanoes refusing to stop for the atmosphere to slowly thicken with CO2 under a frozen sky. A lesser-known real-world detail rests in the rocks that often cap glacial sequences, cap carbonates. In many Neoproterozoic successions, carbonate layers lie directly above glacial deposits, sometimes with the unusual textures and sedimentary structures. Many interpretations link these cap carbonates to rapid chemical shifts during deglaciation, when high CO2 levels, intense weathering, and changed ocean chemistry promote widespread carbonate precipitation. The cap carbonate becomes a pale stone afterimage of melting, a mineral response to a climatic threshold being crossed in the opposite direction. Only took ice retreating for the sea to begin laying down limestone as if it is smoothing over the cold. Yet uncertainty remains in the details of cap carbonate formation. The precise ocean chemistry, the role of alkalinity sources, the timing and rate of deposition, and whether all cap carbonates share the same genesis. The narrative leaves the mechanism open without turning it into a debate because the calm tone does not require closure. The ironies arrive softly dry and sleepy. The first irony is that Earth's climate can be stabilized by feedbacks that require instability. First ice spreads, then CO2 accumulates, then ice melts, as if the planet finds balance by overshooting. The second irony is that even if the surface becomes nearly icebound, the interior remains warm and moving, mantle convection continuing as though nothing visible changes. The third irony is that carbon dioxide can be the agent of both warming and rescue, dangerous in excess, necessary in the right circumstance depending on the planet's state, only took one molecule to play opposite roles across different thresholds. The narrative now holds life within this cold without dramatizing survival. The accepted fact is that life persists through these glaciations because it exists before and after them, and there is evidence of biological activity during and around these times. The details of refugia remain uncertain. If oceans remain at least partly liquid beneath ice, hydrothermal systems continue to supply heat and chemical energy. Microbial ecosystems can persist in dark environments using chemical gradients rather than sunlight. Even in modern Earth, microbial communities exist beneath ice shelves and within sea ice brine channels, demonstrating that ice does not eliminate life's possibilities, though. The ancient global scale conditions would be different. Only took microbes to demonstrate that habitable includes places that look inhospitable from the surface. The quiet scientific mystery here is how severe and long the glaciations are, and how biogeochemical cycles continue under ice. Does photosynthesis persist in open leads or thin ice regions? Does nutrient delivery slow changing productivity? Does oxygen accumulate differently when oceans are capped? Models explore these questions, but the evidence remains partial. The narrative allows that partiality to remain because it matches the larger theme reality as readable, but not always completely. Only took a planet-scale experiment to leave only fragments of the lab notes. The story returns briefly to oxygenation's role, because the timing of major glaciations is sometimes linked to atmospheric transitions. Rising oxygen can reduce methane-weakening greenhouse warming, potentially nudging climate toward glaciation. This coupling is plausible and discussed especially for Paleoproterozoic glaciations following major atmospheric changes. Yet tectonic factors and weathering changes also matter. Continental positions influence albedo and weathering rates. Mountain building affects erosion and CO2 drawdown. Solar luminosity increases over time, shifting baseline warmth. The quiet mystery is not whether each factor has influence, but which combinations dominate at specific times, and why the system crosses threshold when it does. Only took multiple slow controls turning together to make the climate suddenly behave as though it changes its mind. A gentle modern analogy can hover restrained like a balance that remains steady until several small weights accumulate on one side. The climate can hold a state until feedbacks push it past a tipping point. The analogy remains soft because the climate's balance is a coupled set of non-linear equations, not a single lever. The narrative keeps the simulation theme at the edge again, because snowball episodes resemble state transitions in complex systems regime shifts that are difficult to reverse until a counteracting force builds. In computation, one might imagine thresholds, hysteresis, and stable attractors. In Earth science, those same words appear, but they refer to physical feedbacks, ice albedo greenhouse gas accumulation, weathering suppression, ocean circulation changes. The resemblance is again a resemblance of language rather than proof. Still, it feeds the quiet intuition that reality behaves like a system with phases and updates with memory in the form of hysteresis. Only took a frozen planet to make climate feel like it has modes. The narrative ends with a still pale image sunlight falling on the ice that reflects it back oceans dark beneath, perhaps partly sealed, perhaps partly open in places, and volcanic gases rising into a cold atmosphere where weathering cannot easily remove them. Time passes in long spans. CO2 accumulates. At some point, warming begins. The ice-thin sun's darker surfaces absorb more light and the feedback reverses, accelerating melt. Then water returns to rock, weathering resumes, ions flow to the sea and carbonates precipitate, laying down a cap that marks a transition without announcing it. The planet's climate has crossed a threshold and returned, leaving behind deposits that can be read, though not perfectly, and leaving behind life that continues small and persistent. The uncertainty remains calm and unresolved. How close Earth comes to a fully frozen state and how the deep ocean and biosphere behave within that cold. The narrative rests with that uncertainty, letting the ice's brightness fade into the slow continuity of Earth's processes, where even extremes are simply another stable configuration the planet can occupy for a while before moving on. After ice retreats and oxygen becomes a persistent background influence rather than a rare intrusion, life continues to diversify in ways that remain mostly microscopic. And yet the next transformation is one of the most structurally important in the history of the biosphere. Cells begin to contain other cells not as prey or transient infection, but as permanent partners. The accepted fact is that eukaryotic cells arise through endosymbiosis, with mitochondria descended from an ancestral alpha proteobacterium that becomes an organelle inside a host lineage, and this is supported by multiple converging lines of evidence. Mitochondria carry their own DNA. Their ribosomes and membranes show bacterial affinities. Their genes and proteins place them phylogenetically within bacteria, and their double membrane architecture is consistent with engulfment. The narrative remains whisper-soft and stays close to the material reality of it. A small cell within a larger one, membranes touching molecules, moving energy being exchanged. Only took one engulfment that does not end in digestion to reshape the energetic budget of life. The transformation is not a single clean instant in the record. It is a long integration, a gradual knitting together of metabolisms and genomes. Over time, many genes from the endosymbiont transfer to the host nucleus, leaving mitochondria with reduced genomes and making the partnership irreversible because the organelle can no longer live independently. This gene transfer is an accepted process observed across evolutionary history, and it is one reason eukaryotic cells become deeply compartmentalized information and function distribute across nucleus and organelles with protein trafficking. Pathways evolving to move products to where they are needed. A lesser-known real-world detail lingers in the architecture of mitochondria. Themselves, their inner membranes fold into cristae, increasing surface area for the electron transport chain, and the shapes of those folds vary across lineages, reflecting different energetic strategies. It is a quiet geometry of life's power supply, a repeated pattern of membrane thrown into curves because energy production depends on surface area and gradients. Only took a membrane folding inward to multiply the space where electrons travel. The narrative keeps the focus on processes rather than drama. Mitochondria enable aerobic respiration to yield far more energy per molecule of organic substrate than most anaerobic pathways. And this energetic advantage is widely regarded as a key enabling condition for large genomes and complex cellular regulation, though the strength and exclusivity of this relationship are still discussed. Eukaryotes are not defined by oxygen alone. Many live in low oxygen or anoxic environments and possess modified mitochondria or related organelles, but the availability of oxygen as a high potential electron acceptor makes certain metabolic strategies more efficient, and efficiency matters over deep time. Only took oxygen becoming more common for some metabolisms to become more generous with energy eventually. Yet the section's quiet scientific mystery remains central, and carefully held the exact sequence of steps in eukaryogenesis is still debated. Did a host cell with some internal complexity already exist before the mitochondrial merger, perhaps with a cytoskeleton capable of membrane remodeling and engulfment? Or does the acquisition of the endosymbiont come early and drive the subsequent evolution of cellular complexity by providing an energy surplus and new metabolic pathways? Competing models weigh the order of events differently, and the ecological context where this merger occurs, under what oxygen levels, in what kinds of microbial communities, remains partially unresolved. The narrative does not fill the gap. It lets the gap remain like a dim seam in the rock record, because this is one of the places where evidence is abundant in modern cells, but the historical pathway is difficult to reconstruct. Only took more than 1 billion years of microbial life for the most important merger to still have an uncertain choreography. The narrative holds another modern scientific development as a quiet detail. Real and grounded genomic surveys of archaea reveal lineages often referred to as Asgard archaea that carry genes once thought uniquely eukaryotic, including genes related to cytoskeletal and membrane trafficking functions. This supports the accepted broad picture that eukaryotes arise from within the archaeal domain, with bacterial contribution through mitochondria, creating a chimeric origin. Yet the discovery does not write the full script of the transition. It suggests ancestry and capability, not a complete historical scene. Only took sequencing microbes hidden in sediments to make the host cell's identity feel closer and still not fully known. The narrative keeps its elemental imagery by returning to the Proterozoic ocean, because this is where eukaryotes first drift and multiply. The sea is still layered in places with oxygenated surface waters overlying deeper anoxic zones in many basins according to many proxy interpretations, though the extent and persistence of such stratification across the Proterozoic remain debated. In that layered ocean, eukaryotes occupy niches where oxygen and nutrients allow them to maintain mitochondria-driven metabolism, while other environments favour anaerobic strategies. This is consistent with the idea that eukaryotes are flexible but still shaped by redox landscapes. The ocean becomes a quiet map of habitability with invisible boundaries drawn by chemistry. Only took a few micromoles of oxygen difference to define an ecosystem border. The ironies arrive softly dry and sleepy, without changing the flat contemplative tone. The first irony is that complexity in life may depend on cooperation that begins as intrusion one organism inside another, an arrangement that looks like an accident yet becomes the foundation for nearly all macroscopic life later. The second irony is that the most advanced cellular architecture begins in the microbial realm, invisible to casual sight, while the later visible world depends on these unseen structures. The third irony settles quietly. The same planet that constantly erases its oldest rocks preserves in living cells molecular fossils of an ancient merger bacterial genes and membranes, still operating inside every eukaryote, like a persistent signature that tectonics cannot subduct. Only took biology to keep a record that geology cannot erase. The narrative turns to the evidence that eukaryotes emerge in the Proterozoic, because the story remains grounded in what can be supported. Fossils of clear eukaryotes appear by around 1.8 billion years ago in many interpretations, including larger cells with complex wall structures and possible internal organization, though the preservation of nuclei is rare and often ambiguous. Organic-walled microfossils known as acritarchs, many interpreted as eukaryotic algae or related forms, become more abundant later. Biomarkers. Molecular fossils such as strainase derived from sterols have been used as evidence for early eukaryotes, though. Biomarker records can be complicated by contamination and thermal alteration, and their interpretation has been contested in some cases. The narrative holds this carefully. The broad emergence of eukaryotes in the Proterozoic is accepted, while the earliest precise timing and the reliability of some specific signals remain uncertain. Only took a few controversial molecules to remind everyone that ancient evidence can be fragile. A poetic detail rests in the quietness of Proterozoic sediments that hold these signals, thin shales settling in calm basins layer after layer, trapping organic films that darken the rock as if the ocean lays down slow ink. Within those layers, microfossils can be preserved as carbonaceous shapes, sometimes ornamented, sometimes smooth, sometimes spined, each shape a hint of cellular complexity. The spines and ornamentation are not decorative. They may reflect defense buoyancy or life cycle stages, suggesting that ecology is becoming more interactive with grazing predation and selective pressures shaping form. Only took a tiny spine on a cell wall to imply that something else is trying to eat it. The narrative stays slow and allows energy to remain the quiet backbone of the section. Many accounts emphasize that mitochondria provide internalized power production across many small membrane units within a cell, enabling a far larger total respiratory membrane area than would be possible if respiration were constrained to the outer cell membrane alone. This can support larger cell sizes and more complex gene regulation. The accepted part is that mitochondria are central to eukaryotic energy metabolism. The debated part is exactly how essential that energetic shift is as a prerequisite for complexity, and whether other pathways could in principle yield similar outcomes. The mystery is not whether mitochondria matter, they do, but whether they are the decisive enabling factor or one of several necessary conditions that converge. Only took an energetic advantage to become a central hypothesis and still not close the case. A gentle modern analogy can hover restrained, like adding more outlets and wiring to a building allows more devices to run without overloading a single circuit. Internal membranes allow a cell to run more biochemical devices at once. The analogy remains quiet and imperfect, but it suggests why internalization of energy production changes what is feasible. The narrative then touches the wider planet again, because eukaryogenesis does not occur in isolation from Earth's environment. Oxygen levels, nutrient availability, and the redox state of oceans influence which metabolisms are favourable. Phosphorus delivery from weathering ion availability shaped by oxygenation and trace metals that serve as enzyme cofactors can all influence biological productivity and diversification. These links are studied, but reconstructing their Proterozoic dynamics is difficult, and uncertainties remain about how stable oxygen levels are over long spans, and how often oceans shift between more oxygenated and more anoxic states. The narrative keeps this as a calm uncertainty. The environment that hosts the rise of eukaryotes is real, but its exact global patterning through time is still being resolved. Only took 1 billion years of ocean chemistry to leave a record that is indirect and incomplete. The simulation theme remains at the edge, and here it finds one of its most tempting metaphors. Cells begin to look like systems that process information with genomes, regulatory networks, signaling pathways, and compartmentalized modules. Eukaryotic cells in particular exhibit layered control transcription in the nucleus, translation in the cytoplasm, energy production in mitochondria, targeted transport between compartments. This modularity can resemble engineered design when described in modern terms, yet it arises through evolution, variation, selection, drift, and constraint over deep time. The narrative remains strict. Resemblance to design is not evidence of design, and resemblance to computation is not evidence of simulation. Still, a quiet philosophical uncertainty remains, and it is allowed to remain. Why does evolution so readily produce systems that can be described as information processing architectures? And why do physical laws permit such architectures to exist and persist? Only took the language of information to become useful in biology for metaphors to feel close to fundamentals. The section ends by returning to the simplest material scene, a Proterozoic sea, under a sky that contains oxygen, but not yet in modern abundance, sunlight filtering into shallow waters, and within those waters, cells that now contain mitochondria drifting and dividing. Some are solitary, some form colonies, some begin to explore multicellular arrangements that will later become more common. The merger inside the cell becomes a quiet engine that will eventually support larger bodies and more intricate ecologies, but for now it remains microscopic, patient, and real. The narrative leaves the deepest gap open. The exact pathway into this merger remains partly unknown, and the planet keeps the details hidden in the same way it hides its earliest tectonics and its first chemistry of life. Yet the transformation itself is undeniable in its outcome. A new kind of cell exists, carrying within it the trace of an ancient partnership, and reality continues to show its characteristic pattern laws that are consistent structures that are emergent, and a history that can be read in living matter even when stones are silent. The Proterozoic sea remains calm on the surface, yet beneath that calm, the narrative turns toward the act of knowing itself, because Earth's history is not directly watched. It is inferred, reconstructed, measured through limits. The accepted fact is that quantum systems behave differently when they interact with their environments. Decoherence rapidly suppresses observable quantum interference in macroscopic objects, making the world appear classical at everyday scales, even though its constituents follow quantum rules. This is a standard part of modern quantum theory, and is supported by experiments that demonstrate how fragile superposition becomes as systems couple to many degrees of freedom. In this sense, the classical world is not separate from the quantum world. It is the quantum world seen through constant interaction and loss of phase coherence. Only took an environment full of stray interactions to make the universe look solid and definite. The narrative keeps Earth as the anchor, because Earth's rocks are the end products of countless interactions. A mineral lattice is not a pristine quantum system. It is a warm, vibrating assembly of atoms constantly exchanging energy with its surroundings. A grain of zircon in a metamorphic rock is an archive precisely because it is stable in a classical sense, because its bonds and structure resist rearrangement at low temperatures, because diffusion is slow, because the crystal is a stubborn container. And yet at the smallest level, the same zircon is still quantum matter, electrons in orbitals nuclei, undergoing probabilistic decay phonons carrying vibrational energy in quantized modes. This is accepted. Physics solids host quantized excitations and radioactive decay as quantum. The world's classical stability is therefore a kind of emergent stillness, not an absence of quantum behavior. Only took quantum rules being averaged over enormous numbers to create a world that feels continuous. A lesser-known, real-world detail lingers here in the way measurement itself is embedded in geology. In zircon dating, a mass spectrometer counts ions by separating them through electromagnetic fields and detecting them as discrete events. The instrument does not measure age directly, it measures ratios of isotopes, and age is inferred through decay equations. Even the act of measurement is granular, built from counted impacts from pulses from signals above noise. The planet's time becomes a line of numbers because detectors register individual particles. Only took single ions hitting a detector to translate deep time into digits. The narrative does not romanticize this. It observes that knowledge is always mediated. Earth's past is not a film that can be replayed. It is a set of traces that must be interpreted through instruments and models. Here the section's quiet scientific mystery is fundamental. What exactly is measurement in quantum mechanics? Quantum theory provides rules for predicting probabilities of outcomes, and decoherence explains why interference disappears in practice. Yet the transition from a quantum superposition to a single observed outcome remains interpretively unsettled. Different interpretations describe it differently. Some treat wave function, collapse, as fundamental. Some treat it as an update of knowledge. Some treat all outcomes as realized in branching worlds. Some propose objective collapse mechanisms. The math predicts experiments, yet the meaning of one outcome remains debated. Only took a theory that works perfectly in practice to still feel conceptually unfinished. The narrative keeps this mystery quiet and does not turn it into argument. It simply notes that the world's definiteness, this rock is here, this isotope ratio is this number, emerges from processes that are at root probabilistic and relational. The same holds for Earth history. A single proxy is not the past itself. It is a measurement outcome conditioned by a preservation alteration and sampling. A banded iron formation records redox transitions, but it is also influenced by basin chemistry, sedimentation rates, diagenesis, metamorphism. A sulfur isotope signal records atmospheric photochemistry, but it also passes through microbial cycling and burial. A paleosol records weathering under an ancient sky, but it is later compacted, heated, and sometimes partially erased. The accepted fact is that proxies are powerful yet indirect, and that robust reconstructions require multiple independent lines of evidence. The quiet uncertainty is not whether proxies matter, but how to quantify the uncertainties and avoid overfitting a thin record into a too confident story. Only took the planet's habit of recycling and altering its surface to make inference a permanent companion of certainty. The ironies arrive softly dry and sleepy without changing the even tone. The first irony is that the deeper the time, the more the world forces humility. The most important events leave the least direct evidence, while trivial recent events leave piles of detail. The second irony is that humans demand decisive answers about origins. Yet even in physics, the act of getting an answer is itself a subtle process whose meaning is debated. The third irony is that instruments become more precise every decade, and yet the limits of interpretation remain because precision in measurement does not automatically grant completeness of context. Only took better tools to reveal more ways to be uncertain. The narrative returns to decoherence to keep the scientific grounding firm. Decoherence times for macroscopic objects are extraordinarily short, meaning that everyday systems lose coherent superpositions almost instantly because they interact with air molecules, photons, thermal vibrations. This helps explain why chairs do not behave like electrons in double-slit experiments. Yet in controlled experiments, researchers can isolate systems and maintain coherence long enough to observe interference in larger and larger objects, demonstrating that classical is not a separate realm but a practical regime. The accepted process is that isolation preserves coherence. Interaction destroys it. Earth is the opposite of isolation. Earth is interaction at scale. Rocks are pressed, heated, wetted, fractured, altered. Their histories are the sum of countless environmental couplings. The planet is, in a sense, the ultimate decohering environment for its own materials. Only took water heat and pressure to make the past collapse into whatever survives. A poetic detail emerges in the way certain minerals preserve zoning and inclusions, like faint internal landscapes. A crystal can contain concentric bands of composition, each band marking a change in growth conditions, and tiny inclusions of melt or fluid can remain trapped, preserving a sample of ancient chemistry. These are real features studied under microscopes and with spectroscopy. They feel like snapshots because they are preserved states, but they are also the survivors of a long selection process. Countless other crystals dissolve, recrystallize, or are subducted and lost. Preservation is not guaranteed, it is contingent. Only took one grain being in the right place at the right temperature to become an archive. The narrative keeps the simulation theme at the edge where it belongs, because measurement limits and information language often feed it. In physics, information has quantitative meaning. Entropy can be related to the number of microstates. Quantum information measures correlations. Black hole thermodynamics links area to entropy in ways that suggest deep connections between geometry and information. These are real research domains. Yet none of this directly implies that the universe is running on an external computer. It implies that information is inseparable from physical state counting, and from what can be distinguished. The quiet uncertainty is what is truly fundamental. Are space-time and matter primary, with information as a description, or is information primary with space-time emerging from deeper informational structure? The debate is active with no final consensus. Only took two plausible ontologies to keep the foundations unsettled. The narrative returns again to Earth's practice of inference because it offers a grounded analogy for how knowledge works without claiming more than is warranted. When geologists reconstruct an ancient ocean's oxygenation, they do not see oxygen. They see iron minerals, sulfur isotopes, trace metal patterns, fossil assemblages, sedimentary structures. They integrate, they model, they test consistency across records. This resembles in a gentle way how physicists infer quantum states from measurement outcomes, never seeing the state directly, only its statistical footprints across experiments. The analogy remains gentle because the domains differ, yet the epistemic structure is similar. Reality is accessed through interaction and record. Only took reality being accessible only through traces to make inference a universal method. A lesser-known detail rests in the way uncertainty is formally handled. In geochronology ages come with error bars that reflect analytical precision, calibration, uncertainties decay, constant uncertainties and geological complexities like lead loss or inheritance. In climate reconstruction proxies come with uncertainties from diagenesis, spatial coverage and interpretation. In quantum experiments, outcomes come with statistical uncertainties, systematic errors and model assumptions. The presence of uncertainty is not a weakness. It is a measurement of honesty. Yet the quiet mystery remains, even if uncertainties are quantified. Do they capture all the unknown unknowns, especially in deep time, where the record is incomplete? Only took an unrecognized bias to move an entire reconstruction. The narrative then slows into the concept of coarse graining, because coarse graining is how macroscopic laws arise. Thermodynamics works because microscopic details are averaged into bulk variables like temperature and pressure. In geology, coarse graining happens naturally. Fine details are erased, leaving only robust large-scale patterns. A mountain belt records convergence, not each individual grain boundary's history. A banded iron formation records redox cycling, not each local microbial event. Earth is a coarse-grained historian of itself. This is accepted in the philosophy and practice of earth science. The record preserves some variables and loses others. The quiet scientific mystery is how much of Earth's early history is in principle recoverable and how much is fundamentally lost, because the physical processes that create record also erase information, increasing entropy. Only took time itself to be the ultimate data loss mechanism. The section ends by letting the listener's attention rest on a simple scene that joins these ideas without forcing a conclusion. A thin layer of mud settles on a Proterozoic seafloor. Grains align, pores fill with water, microbes metabolize in the dark minerals, precipitate ions, diffuse. Over time the layer becomes rock. It is measured much later by the instruments that count ions and photons, by theories that describe probabilities and decoherence, by models that translate traces into histories. The rock does not contain the whole past. It contains what survives the planet's own filtering. Reality in this view is not a clean feed of perfect data. It is a lawful process that leaves imperfect records. Simulation theory remains difficult to dismiss for some minds because the world seems describable in information terms and because measurement feels like an update from possibilities to outcomes. Yet the narrative remains anchored. Measurement is a physical interaction. Decoherence is a physical process, and Earth's proxies are physical traces. The deepest unanswered questions remain open. What measurement ultimately is, what is fundamental beneath space-time, how much of the past can truly be recovered, and the planet continues indifferent and steady, leaving new traces and erasing old ones, a vast system where knowing is always an act within the world, not a view from outside it. The narrative now stands at the edge where physics becomes interpretation, and it stays calm there because this edge is not a cliff. It is a shoreline, and the water is made of definitions. Earth continues its slow processes in the background, plates moving oceans, circulating air, exchanging molecules with stone, while the mind introduces a question that is modern in phrasing, yet ancient in impulse. Is reality more like a world that simply is, or more like a world that is computed? Simulation theory enters here not as an announcement, but as a lens that some people hold up to the laws already described: quantization, probabilistic decay thresholds, information-like traces, and the strange fit between mathematics and nature. The narrative keeps scholarly caution as its spine, because the accepted fact is that simulation theory as commonly discussed is not a scientific theory in the same way plate tectonics or quantum electrodynamics are. It is largely a philosophical hypothesis, unless it makes testable predictions that differ from non-simulation physics. Only took a compelling metaphor to be mistaken for evidence sometimes. The narrative lingers on what makes a claim scientific. A claim becomes scientific when it constrains what can be observed, when it risks being wrong. Physics does this constantly. A radiative transfer model predicts a spectrum, a mass spectrometer reading predicts an isotope ratio. A tectonic reconstruction predicts where certain rock types should appear. In each case, the world can refuse the prediction. Simulation theory in its strongest popular forms often struggles here, because it can be made compatible with almost any observation. If something is seen, the simulation includes it. If something is not seen, the simulation excludes it. This flexibility makes it hard to falsify. Yet there are versions of the idea that try to move closer to science by proposing detectable artifacts, limits, discretizations, anisotropies, computational constraints that would show up as deviations from expected physical behavior. The narrative stays careful. Proposing a test is not the same as having evidence, and many proposed signatures can also arise in ordinary physics without any simulation premise. Only took one ambiguous anomaly to be interpreted as a glitch by the impatient. The accepted fact that anchors this section is that physics already contains discrete structure and limits without invoking simulation. Quantum mechanics quantizes energy levels and fields. Relativity limits information transfer to the speed of light. Thermodynamics links information processing to energy dissipation. And quantum information theory constrains copying through the no-cloning theorem. These are established results. They can be described in computational language, but they do not require a literal computer. The narrative holds a quiet scientific mystery here that remains unresolved and relevant. What is the fundamental substrate of reality? Is it quantum fields on space-time, or is space-time emergent from entanglement and information? Or is there a deeper unified framework in quantum gravity that changes the terms entirely? This is an active frontier, and until it is resolved, metaphors of computation and metaphors of geometry can both feel plausible. Only took the foundations of physics being unfinished to keep metaphors alive. A lesser-known real-world detail arrives from the practical side of physics rather than the philosophical side in precision tests of fundamental symmetries such as Lorentz. In variance, scientists look for tiny deviations in how particles behave at high energies or across different directions in space. Many experiments and astronomical observations place extremely tight bounds on such violations. This is real and ongoing. If space-time had a simple lattice at some scale, it might introduce preferred directions or energy-dependent speeds of light that could in principle be detected. And so far strong constraints exist on many such effects. The narrative does not claim that this rules out simulation. It only shows that nature as measured preserves certain symmetries with remarkable fidelity, making naive pixel grid notions less likely. Only took reality being consistent to make sloppy simulation imagery look less convincing. The narrative keeps Earth as a grounding object because Earth's history demonstrates that lawful complexity does not require external authorship. Plate tectonics looks algorithmic because it is cyclical and rule-driven, but it is powered by heat flow and buoyancy. Oxygenation looks like an update because it crosses thresholds, but it emerges from feedbacks among sinks and sources. Snowball transitions look like regime changes, but they are ice albedo and carbon cycle physics. In all these cases, the language of computation can be useful for modelling, but the underlying processes remain physical. A gentle modern analogy can hover restrained like using a computer model to forecast weather, does not mean the sky is running software using computational descriptions of nature does not imply nature is itself a simulation. Only took a good model to tempt the mind into confusing map and territory. The ironies arrive softly dry and sleepy without any sharpness. The first irony is that simulation theory often points to quantization as evidence of a grid, even though quantization is simply what quantum mechanics predicts and tests confirm, and it does not come with a built-in pixel lattice in ordinary space. The second irony is that the more the world is measured, the more it looks lawful and compressible, which can make it feel engineered even though lawfulness is exactly what physics expects in any universe that can be studied. The third irony is that a hypothesis that explains everything can end up explaining nothing because it refuses to tell the observer what should not happen. Only took an idea becoming too flexible to lose its scientific teeth. The narrative now weighs what can and cannot be dismissed in a quiet tone that respects both curiosity and discipline. Simulation theory cannot be dismissed as pure nonsense in a broad philosophical sense, because it is logically possible that a sufficiently advanced civilization could simulate environments and minds, and it is also logically possible that observers could be inside such a simulation without direct awareness. But logical possibility is not the same as empirical support. Science does not operate by cataloguing all logical possibilities. It operates by testing constrained models against data. The narrative therefore holds a careful distinction. It does not dismiss the simulation hypothesis as impossible, but it also does not elevate it to a scientific conclusion. It sits in a category of ideas that may remain undecidable unless it becomes testable in a way that differentiates it from standard physics. Only took a hypothesis being compatible with all outcomes to make it hard to confirm and hard to refute. The narrative lingers on what testability might mean in this domain without inventing claims. If reality were computed with finite resources, one might imagine constraints such as maximum information density, limits on resolution, or detectable discretization. Yet physics already contains limits, like the Bekenstein bound and holographic ideas that relate information content to area, and these arise from black hole thermodynamics and quantum gravity considerations, not from an external computer assumption. In other words, information limits are not unique fingerprints of simulation. They are already part of mainstream theoretical physics discussions. The quiet scientific mystery remains whether these information bounds point to a deeper informational foundation of space-time or simply reflect how gravity and quantum mechanics constrain states. Only took black holes being strange to make information feel fundamental. A poetic detail appears here in the way light carries the world's state outward. A planet emits infrared photons that encode its temperature field. A star's spectrum encodes its elements. A rock's isotopes encode its history. The universe is full of encodings because physical interactions imprint correlations. It is a quiet beauty the world writes itself into the particles it releases. This can look like computation because computation is also about encoding and transforming information. Yet correlation is not code in the human sense. It is simply what happens when systems interact. Only took contact between things to create messages without messengers. The narrative then returns to the deepest emotional neutrality it does not need a verdict to continue. It notes that simulation theory often arises from two feelings that are scientifically respectable as questions: why is the universe comprehensible and why does mathematics fit? These remain open in philosophy of science, but they are not solved by declaring simulation, because a simulation would still raise the question of why the simulator's universe is comprehensible and why its mathematics works. The explanatory burden shifts outward without disappearing. Only took one why to generate another why beyond it. The narrative keeps Earth's transformations in view as a counterweight to metaphysical drift. Earth does not behave like a stage set. It behaves like a thermodynamic system with history, irreversibility, and constrained possibilities. It erases data through entropy and tectonic recycling. It preserves data through stubborn minerals and layered sediments. It produces life through chemistry and selection, then alters its own atmosphere. These processes are sufficient to account for much of what is observed without invoking an external computational layer. Yet there remains a calm and honest uncertainty. The foundational nature of reality is not fully known, and some interpretations may remain beyond direct test. The narrative allows that uncertainty to be present without treating it as an invitation to fill the gap with certainty of any kind. Only took humility to be an appropriate stance at the foundations. The section ends by letting simulation theory rest where it belongs in this series as a metaphor that can sharpen attention to discreteness, information, and limits, but not as a replacement for Earth history or physics. The planet continues, and whatever reality's substrate ultimately is field's geometry, information, something not yet named, it expresses itself as consistent processes that leave traces. The ocean still moves heat along density surfaces. The crust still rewrites itself. The atmosphere still shapes light. Life still copies and adapts. The deepest questions remain open not as a failure but as a natural boundary of knowledge in a world that is larger than any single description. Reality in this calm view does not need to be dismissed as simulation or confirmed as non-simulation to remain what it is, a lawful material continuity that can be modelled, measured, and still not fully reduced to a final explanation of why it is so coherent in the first place. The narrative returns from the shoreline of interpretation to the weight of the planet itself, because Earth is the most honest answer to questions that drift too far. It persists. Stone remains stone. Water remains water. Light arrives and leaves. Time continues to move in one direction, carrying heat outward, carrying isotopes toward their daughters, carrying coastlines through cycles of erosion and deposition. If reality is computed, it still must render these consistencies. If reality is not computed, these consistencies still hold. The accepted fact is that physical laws as currently understood are remarkably stable across time and space. The same atomic transitions that produce spectral lines in a laboratory appear in distant stars and galaxies. The same gravitational dynamics that shape tides govern planetary orbits. These same thermodynamic principles govern engines and mantle convection. This stability is what makes science possible. Only took nature being consistent for knowledge to accumulate instead of resetting every morning. The narrative stays whisper soft and lets that consistency become a calm presence rather than an argument. Earth's history is a sequence of transformations that can be reconstructed because the rules do not change capriciously. Radiometric decay rates remain constant enough to date ancient zircons. Mineral phase boundaries remain consistent enough to infer pressures and temperatures. Fluid dynamics remains consistent enough to understand ocean circulation and atmosphere. Biology remains consistent enough that genetic relationships can be traced. This is accepted. The unity of physical law across domains is the foundation of the scientific worldview, yet a quiet scientific mystery remains within this stability, and it is one of the deepest. Why are the laws so stable and so mathematically expressible? The narrative does not pretend to answer. It simply notes that this mystery exists whether or not simulation is considered, because even a simulated universe would require underlying stable rules in the simulator's reality. Only took the question moving outward to show that it does not disappear. A lesser-known real-world detail rests in the way Earth's stability is not absolute but bounded. Some constants are tested for variation across time, such as the fine structure constant, by examining spectral lines from distant quasars, and by studying natural nuclear reactors like the Oklo reactor in Gabon, where fission reactions occurred around 2 billion years ago, and left isotopic evidence that constrains changes in fundamental parameters. These studies place tight limits on variation suggesting strong stability. The narrative holds this gently. Earth itself, through an ancient natural reactor, becomes a laboratory for checking whether the rules drift. Only took uranium reaching criticality in the past to become a test of whether physics stays the same. The narrative then returns to Earth's physical persistence as a quiet rebuttal to the temptation of treating the world as mere appearance. Simulation talk can sometimes thin reality into something less tangible, but Earth's processes remain materially constrained. Plate tectonics requires heat flow and density contrasts. Oceans require water and gravity. Atmospheres require gases and escape processes. Life requires chemistry and energy. These constraints are not aesthetic, they are measurable. The planet's transformation pathways are not arbitrary. They follow thermodynamics and kinetics. They are shaped by feedbacks and they carry irreversibility. Only took entropy to ensure that history leaves scars instead of clean loops. The narrative keeps its dry, sleepy ironies, 3 of them, without changing tone. The first irony is that people reach for exotic explanations like simulation while standing on a planet that already behaves like a marvel of a lawful complexity, needing no extra layer to be astonishing. The second irony is that the most philosophically unsettling questions, why laws exist, why constants have their values, do not go away when simulation is added. They simply relocate. The third irony is that a universe that might be simulated would still need to obey internal consistency, which means the same patient work of science would still be the best way to understand it. Only took curiosity to remain useful in any metaphysical scenario. The narrative now slows further and returns to the series motifs in a gentle, continuous weave, not as summary but as resting imagery. Dust becomes rock through accretion and differentiation, and rock becomes crust through cooling and melting, and crust becomes continents through tectonic persistence. Water condenses into oceans and circulates through basalt and granite, carrying ions and heat. Light scatters in air and is absorbed by molecules shaping climate. Time is counted by radioactive decay, and time is given direction by entropy. Life begins as copying chemistry and becomes a planetary force through oxygenation and nutrient cycling. Eukaryotic cells arise through merger, internalizing energy production and enabling new architectures. All of these are accepted in broad outline, and each contains uncertainties in detail, exact timings, mechanisms, threshold sequences. The narrative does not try to close those uncertainties. It lets them remain as the natural edge of what can be known. Only took deep time to make certainty, expensive and partial knowledge, still meaningful. A gentle modern analogy can hover one last time restrained and calm. Earth is like a vast book written in a language that repeats its grammar reliably, even though many pages are torn out and many sentences are smudged. The analogy remains soft because Earth is not a book. It is a system of matter and energy. But the sense holds there is structure that can be read and there is loss that cannot be recovered. Only took plate tectonics and weathering to act like an editor with no interest in preservation. The narrative now approaches stillness, preparing for the wind down that follows, removing forward motion without making conclusion. It rests with the idea that reality is not easily dismissed because it is consistent, and it is not easily simplified because it is layered. Simulation theory remains in this calm view as a philosophical possibility and a provocative metaphor, not as an established scientific conclusion. It cannot be dismissed as logically impossible, but it also cannot be treated as confirmed without distinctive evidence. In the meantime, Earth remains a tangible reference, a planet whose history is measurable through isotopes and minerals whose processes can be modelled by physics, and whose living systems can be traced by molecular evidence. The world's coherence is enough to study, and its mysteries are enough to keep open. Only took the planet continuing to exist to keep the inquiry grounded. The narrative ends this section with an image of the present Earth held in deep time perspective. Night falls over an ocean that has circulated for billions of years. The moon rises still receding, still pulling tides that lay down thin layers in quiet bays. The atmosphere holds gases whose ratios have shifted through long transitions, and it filters starlight that arrives from distances large enough to make human time feel brief. Rocks cool and crack, rivers carry ions to the sea, microbes metabolize in sediments, forests and deserts exchange carbon with air. The planet's surface is not static, but it is steady in its obedience to law. Whatever the ultimate substrate of reality, this steadiness remains the most immediate truth. The narrative leaves the last unresolved question where it belongs, quiet and unforced. Why there is something rather than nothing, and why that something is so coherent. No verdict arrives. Only the continued turning of a real-world patient and measurable inviting attention without requiring certainty. The rhythm slows further now, and forward motion softens until it is almost indistinguishable from stillness. Earth remains present, not as an argument but as a physical hushstone cooling in night air, water holding heat and releasing it slowly, clouds thinning and gathering again without intention. The planet's deep mechanisms continue mantle convection, tidal friction, radioactive decay, but they do so beneath perception, like a quiet machinery that never needs to announce itself. Only took billions of years for the most important processes to become background. The ocean continues to circulate along density layers, carrying traces of salt and temperature, carrying dissolved carbon and sulfur, carrying the memory of past climates in slow-moving currents. The atmosphere continues its exchange with the sea and land, a thin, restless skin that is mostly empty space, yet capable of warming a world through a few molecules that absorb infrared light. The moon continues its outward drift, and the day continues its gradual lengthening, a reminder that even the most familiar unit of time is not fixed. The world remains lawful, and lawfulness remains the quiet condition that makes anything knowable at all. Only took nature being consistent for questions to persist across generations. The question of simulation now becomes less like a claim and more like a distant echo, a way the mind tries to hold the strangeness of a coherent universe. Whether reality is computed or not, the same immediate facts remain. Energy flows, entropy increases, gradients form and relax, structures emerge and dissolve. A rock does not become less real because it can be described as information. It remains a lattice of atoms that resists pressure, fractures, weathers, and holds isotopes in ratios that change predictably through decay. A living cell does not become a metaphor because its genome can be counted in bits. It remains chemistry that copies, repairs, and metabolizes driven by gradients across membranes. Only took language becoming powerful for it to tempt confusion between description and substance. The atmosphere dims toward midnight. Starlight arrives as ancient photons, each one indifferent to the stories told about it, each one simply an interaction waiting to happen. The planet receives that light, absorbs some, reflects some, and radiates its own infrared, outward into space, a steady exhale that never stops. Far beyond any coastline, beyond any mountain, beyond any laboratory, the universe remains vast and quiet, and the foundations remain partly unresolved. Why constants have their values, why the arrow of time exists, what measurement ultimately means, whether space-time is fundamental or emergent. These questions remain open without needing a conclusion. Only took honest uncertainty to be compatible with calm. The narrative releases the need to move anywhere else. It rests with the simplest elements: dust that becomes stone, that becomes sediment, that becomes rock again, water that rises and falls in cycles, light that arrives and departs, time that passes in one direction. The planet continues to turn through darkness and into morning and back again, repeating the same lawful motions while changing slowly underneath them. Nothing needs to be solved in order for the world to continue. The surface cools, the ocean quiets between waves. The air settles into a soft pressure against everything it touches, and in this steady physical presence the mind can let the largest questions remain what they truly are not. Emergencies, not puzzles that demand resolution tonight, but wide horizons that sit beyond the edge of certainty while Earth remains here tangible, patient, and quietly real.